Tja, tja. Zo, ja, ja, ja. Hey, 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 hey. Hey, 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 hey. Hey, 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 hey. Ta-ta, ta-ta, ta-ta. Ta-ta, ta-ta, ta-ta. Ta-ta-ta-ta-ta-ta-dum. Ta-ta-ta-ta-ta-ta-dum. Ta-ta-ta-dum. Zo, 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 zo. Ta-ta, ta-ta. Ta-ta, tja. Zo. Ta-ta. Zo, ja, ja, ja. Ta-ta. Zo.
Sorry? Ja. Ja.
Test, test.
All right, let's get started here. Thank you everyone for joining us, and we're pleased to have our first talk today by Tanmay on Open Policy Agent. So let's welcome our speaker.
Thank you, Matt, and thank you everyone for coming. So this is going to be a short talk on Open Policy Agent. So the Open Policy Agent package helps us to enforce policies in applications. Before we start, a short take on what do we mean by a policy. So policies are rules which we can query. We can pass input, provide some inputs when we query. The policies themselves may have access to some data which is static, and with all of these, the policies can evaluate a decision, and that's the decision in which we are interested in. So to give an example, let's assume we have a system, a counting system, where users can log in, but only logged in users are allowed. And since it is sensitive, it's not going to allow anyone outside office hours, and except the boss, who is allowed at all times. But when an audit is going on, only the auditors can access. So you see how the rules build up. They build up in complexity, and they may also change over time, and new rules may get added, old rules may get changed or removed. So it's a bunch of things, right? And the motivation of like having a policy engine is usually when you build something large, the people who want to set these policies or change these policies, and the people who are doing the rest of the stuff, they are usually not the same. Okay, so you want something separated so that the concerned people can be changing the policies while we can just use the policies, right? So that is where OPA comes in. So OPA is a rules engine or a policy engine. It uses this high-level declarative language called Rego to define policies, which lets us like do policies as code. And it has a very simple APIs, which makes it easy to integrate the engine into applications. And it helps in obvious ways. So it offloads the decision making to a separate component while keeping the enforcement within your business logic, and which leads to simplification. It simplifies compliance because now policies can be centralized, decision making is centralized, audits are simpler, and integration is easy because it is API based. It can be used as a library or a service, and so easy to integrate at any point, any enforcement point. So Open Policy Agent is the package which brings all these goodies to be used easily in Julia. It encapsulates OPA. OPA is the Open Policy Agent for Julia applications. So it has a few modules. The service module, which is the engine itself, the decision-making engine. The client, which we use at the enforcement points. And it also encapsulates the CLI, the OPA executable as a tool. And there is this fourth thing that I mentioned, which is a plugin to consume partial evaluation result. Now, this is a very interesting and powerful thing. We will see that in a little bit. We'll see. Explain that. So the service module helps in starting OPA as a service. It monitors failures and restarts and keeps it running. And the client is essentially an Open API or REST client, which we can use it at different points in our application at enforcement points. The CLI, as I mentioned, wraps the OPA command line, and all the command line commands are now available as Julia methods. The example of how we can use it. Yeah, and now coming to this interesting point of partial evaluation. So it is possible to query OPA policy by not giving it the entire set of parameters it is expecting. We can only send a part of the values it needs to evaluate a rule. And what OPA will do is, if using those partial values, if it is able to arrive at a decision, it will return that decision. But if it is not able to arrive at a decision, it is going to give a partially evaluated, simplified rule. Okay. So the simplified rule can be again evaluated later with more data. It can be taken to a new place, evaluated. It is in the form of a AST, and it can be then transformed to a different form, which is useful. So what we have in Open Policy Agent is a way to plug in processors for this AST, right? So in Open Policy Agent, we have included a processor for converting these partially evaluated rules to SQL conditions, where conditions, because we needed to evaluate that in a database. We shall see we shall see a demo of that. Sorry? Okay. All right, so here I just start using the package, and this is the policy. This is the policy for the same accounting system I spoke about, I gave an example about. So no one is allowed by default. These are the business hours. Allow all users during business hours. And the boss is allowed at all hours, but only when audit is not happening. And allow only auditors when audit is happening during business hours. So this is our entire rule set written in Rego. We start a OPA server, and then we create a client to interact with the OPA server. And this is where I'm initializing the policies in the OPA server. This is not the usual way how things are done. Usually the server itself will be configured with the policies. But since it's a demo, this is easy to do as well. Now, this is a method that queries our policies and then gets the result. And you can see I'm using partial results. And I'm going to transform that to something useful that we'll see. Right? So this is our method. Now everything is ready. We can query our policy engine. Let's ask if users are allowed during business hours when there is no audit. Users who are logged in, audit is false, and they're trying to log in at 10 o'clock on a Tuesday. And they are allowed. Are users allowed 1 o'clock in the night? They're not. Is the boss allowed at the same time? Yes. But is the boss allowed when there is an audit? No. And this is the interesting bit. We can also query it to find the list of users who are allowed to access during an audit. And it is going to give a partial result, which we can now change to some form like this. So it says if the role is auditor, then it is allowed. Similarly, we can find the list of users who can access outside business hours. It's the boss.
I missed this room.
Yeah, so that's all I had. If I have time, I can take questions.
Great. Let's thank our speaker. We just have time for one quick question while the next speaker begins setting up. You can come set up. Yes.
I would be interested to go down something like this.
One moment. Sure.
Thank you.
So that doesn't do anything.
I think it's for the online audience.
Okay. So I'd be interested in this, not so much for from a legal standpoint, but maybe more in technical safety applications. For example, one thing like you have a particle physics beamline, and everybody must be out, and all the keys must be returned before the beam can turn on, or the high voltage can only turn on in the lab if somebody tells the high voltage power supply turn on.
Yeah.
And then the power supply asks, am I allowed to actually turn on? Is this something that can map to these things?
I think so, yes. You can write rules and then if everything is programmatic, it makes sense, yes.
Great. Thank you. Let's thank our speaker one last time. With that, pleased to introduce our next speaker. Please come in, sit down. Our next speaker is Mikola Lukakchuk on exponential family manifolds. Thank you so much.
Yeah, hi everyone. Way bit short of time, but sorry my fellow Bayesians, I will start just throw heads with some maximum likelihood example, which I suppose everyone should understand. You have some parametric model, parameterized with parameter status. You have some data, and you will just maximize likelihood. Yeah, we take in log. Usually it works. Should be fine implemented for base of distributions in distributions.jl? No? Yeah, and if you will try for some basic distributions, probably, I suppose you are like a fellow Julians, you know how to use forward diff, optim, you write your likelihood function, like just log PDF over your matrices, and you want kind of naively run optimizer over it. And should it work? Yeah, obviously no, because then there will be no point for my talk. Yeah. It will fail because, yeah, Cholesky decomposition failed. And why? Because Wishart second parameter, Wishart has two parameters. One is degree of freedom, probably you know, and second is a scale matrix, which is positive definite matrix. And if you will run just naive Euclidean optimization, you will bump out of your constraints. That actually, with probability 1, I would say. And yeah, that's kind of a problem, but there is a solution. We have a great ecosystem of manifolds.jl, and I'm really grateful for Ronnie Bergman and all collaborators in manifolds.jl that they are supporting it. And you can think about manifolds.jl is a kind of, what is a manifold? What the heck is a manifold? It's just, you can think about it just like a set with at each point you have a just vector in which one you can follow, and some n retractions. That's actually baby steps through our manifold. And what the heck exponential family manifolds? Yeah, it's just implementing for each distribution, for example, for Wishart. It's like a wrapper around manifolds.jl that just implements for parameters of a Wishart or for parameter for another distribution, it's manifold of its parameters. And you can sample some point on this manifold, you can do a step and accord in some direction, and that's basically it. And yeah, you can right now can ask me, but sorry, Mikola, but what is exponential family? You explain us what is a manifold. Yeah, exponential family distributions is just some special case of a distribution, and Wishart, for example, it is. And they are particularly interesting for me because products are defined for it. And there is a huge ecosystem already in Julia called exponential family.jl that actually implements a lot of basic functions around exponential family distributions. And yeah, right now, great seeing that first, Wishart fast is specific representation of Wishart in exponential family representation that I just showed. And yeah, great, we right now can run gradient descent over our likelihood for Wishart. Thanks, manifolds.jl. And kind of to put it in a bit broader ecosystem, there is exponential family.jl that implements basic functions like products, means, grad log partition, and so on. And there are exponential family manifolds that implement manifolds of parameters smooth constraints. And there is also exponential family projections, on which I don't have time to talk about, but it's actually if you have some strange log PDF and you want to present it in some nice, well distribution as a Wishart, you can project your log F onto this distribution. And how I would not say, I'm from a bias lab, probably Yosoki know from BERT, if not, please watch. There is a RxInfer. RxInfer is a package that basically automates Bayesian inference, and it doing it basically through exponential family distributions, basically through the products. And for example, we see some simple normal mean variance model. We have normal prior, normal likelihood. If you will multiply normal likelihood and normal prior, you will just obtain once again a normal. And as you see, RxInfer works. But what will happen if you will put a better prior? Yeah, we see our axis is no 0.5 and no 0.6. So it kind of makes sense that our posterior should be centered somewhere. Maybe you have some prior information, or maybe you just want to try centering it at a 0-point interval. So you put a better prior, but will it work? Well, no, because product of beta distribution and normal is not defined in exponential family. But what we can do, and I hope you already understand that it's a talk about optimization, so that every problem should be solved with optimization. And we already know our space. It's a space of exponential family distributions, and we just need to find objective. Please watch Bert talk. The objective is free energy. And yeah, free energy, yeah, it's in other terms, it's KL divergence, maybe, you know, it's like that. And exponential family projection, it just implements only one class. It's this KL projection, and project 2 is a way kind of to solve this problem. And yeah, what I'm doing here, I am extending my product between beta and Gaussian through projection on beta family. And once again, the product works. Your posterior are computed, all problems solved, you can conquer the world. Thank you, and I'm ready for the questions.
Okay. Okay. Hello. Thanks for keeping on time. So I think we are a bit late on the schedule, so we will have time maybe for 1 or 2 quick questions. So.
Hi, thanks for the very nice talk. You said you will do gradient descent. Can you also do kind of like quasi-Newton or something like that directly?
Yes, you can. Yeah, basically, project interface is this project 2 interface here. It can accept different optimizers. So you can run gradient descent or quasi-Newton or whatever great package manifolds.jl implements. Yeah.
Okay, thank you very much.
Thank you. Thanks, Nicola. I think we have to get to the next talk because we're behind schedule. So the next talk, well, the next presenter connects his laptop. I think it's blasphemy, right?
Yes.
So Sebastian, you're from university from Toronto.
Yes.
Toronto. Okay, thanks for flying by.
Oh, sure.
I will not distract you. Please connect your laptop. Half an hour, right?
Sorry? Yes,
Okay.
that's what I was told at least.
Yeah. Okay. I will show you 5 minutes and 1 minute before.
Yeah, okay, sounds good.
Okay. Okay, then I will let you get started. This looks very interesting talk.
Okay, hi. Thanks all for coming to my talk about blasphemy. It's a project I've been working on last year during my internship in a Julia lab. And it's about improving enzyme and autodiff tool, which is quite used in the Julia land nowadays for linear algebra routines, which are obviously used a lot for Julia. So about my collaborators, I started last year.
Talk to the microphone, otherwise it's...
Oh, yes, for the online people. Yes. Sorry. Yeah, so those are my collaborators since last year. Billy has taken over the project a few months ago. And yeah, the other colleagues obviously also have. Now, for those who don't know so much about AD, that's how AD in most languages looks like. You have source code overloading, source code rewriting. So no matter if you have C++, Julia, Rust, or whatever, your tool takes some source code in, produces a new function or some new source code which computes gradients for you, which is great because you don't want to apply the chain rule to large functions yourself, right? That's just error prone. So let software do the job. Now, obviously, all those languages have a compiler backend. In the case of Julia and a lot of other languages, it's LLVM. LLVM is going to optimize your code and generate a binary for you. Pretty great, except now every single language out there has to implement their own AD tool, which isn't that great after all. There's a second issue with that, which I show in this case study, vector normalization. So your compiler implements a lot of optimizations for you. Whatever code you write, that's not what ends up in a binary. So here, let's assume we compute the magnitude. It's a super primitive approach. Let's say we loop over each element and we divide by the magnitude of our vector. Now, computing the magnitude is O of n, looping is O of n, we O of n squared in total. Obviously, this is pretty naive because our whole input vector is not going to change at all during the whole computation. So it's loop invariant, right? So there's a optimization path called loop invariant code motion, which does kind of what the name says. It moves invariant computations out of a loop. So now suddenly you have O of n, which is great, right? Now there are some issues if you do source code AD with those cases. Because let's look at this pipeline. We now first apply our loop invariant code motion. We have O of n, we differentiate it. That's under reverse mode AD, which is the most common one. Details don't matter so much, but effectively we rewrite your code. And obviously rewriting your code might introduce some new data dependency. Here everything is fine. You have a simple loop. We rewrite it. It's still a simple loop. Now what happens if we go for source code rewriting? That's effectively the lower half is what all the other AD tools out there do which work on a source language. So they don't have any optimization passes available because no compiler is optimizing source language. They all optimize intermediate representation. So now you rewrite your source language and suddenly you introduce some new data dependencies for the computation of your magnitude. Now that's pretty bad because now you see dres is something which is computed in the previous step. It's computed based on the loop variable I, so now it's not loop invariant anymore. So that's bad. Now, whatever you do as an optimization pass, you can't really move it out of the loop anymore, right? So here you suddenly end up with O of n squared instead of O of n. So there are a lot more of these optimization passes, but at the end of the day, what Enzyme does is we first let your source language be compiled down to LVMIR, and from there on we optimize, run AD, and optimize again, just to be sure, before we generate your binary. Now, so yeah, we did run a couple of benchmarks, Enzyme after running optimizations, Enzyme before running optimization, against some other tools, and effectively, it's kind of what might be known in the GLN nowadays. Enzyme is quite fast in the majority of cases. So it looks like it's a great start to differentiate some linear libraries, right? But what if that's not true? Do we really want to rewrite linear algebra libraries? Because BLAS, for example, basic linear algebra subroutines are not your average code. That's not what like any of us here would write, right, in our day-to-day job. So maybe we should reconsider. For those, like, let me just give a quick introduction about how BLAS works in JuliaLand. So you do have a couple of matrix and vector types, and if you do operations on them, generally they are going to get lowered into BLAS calls. So someone else implemented them for you. You don't need to re-implement them. They're quite optimized. They are multi-threaded. If you're lucky, you get an optimized version if you have a supercomputer for specifically your hardware. And I mean, if you look at Intel MKL, for example, that's closed source. So for Enzyme, that's a bit tricky, because if you just give us a binary, some assembly, we don't really know how to differentiate that, right? But we can replace your black box call to some linear algebra library which we understand. So what we do and what we did for a couple of years in enzyme.jl is every time you load a BLAS library, we just unloaded it and load our own BLAS library. Sorry. So there are a couple of issues, as you can imagine. It might be slower because we always load the same OpenBLAS version, no matter what supercomputer you have. It's single-threaded because multi-threading is complicated. We don't want to deal with that, right? And it works, except when it doesn't. So what issues do we have with correctness? There's GEMV, which means general matrix vector multiplication. It's a super simple thing. You have a matrix and a vector, right? What can go wrong? Apparently a lot, because BLAS routines nowadays have a lot of short path. So if you know that one of your dimensions is 0, you know that you don't really have to do any computations, right? So you return early, which is totally fine for your primal. It's not so much fine if you want to compute gradients, because the way in which those functions get rewritten basically introduce error cases. So that's what we had as an answer back then. We simply removed this optimization from our BLAS library. So it's not only we gave you a generic library, single-threaded, which is slow, we also went ahead and removed some of the optimizations from that BLAS library. So you can imagine how fast that ended up being, right? Yeah, we were at least honest about it. You got a couple of these issues every time you try to differentiate a BLAS routine using Enzyme. And as a result, obviously, people created issues about, hey, surprisingly, or not surprisingly, enzyme.jl is slow on BLAS. What can we do about it? We did some benchmarking also. Pretty much as you expect, if you have a single-threaded BLAS library, it doesn't really benefit from your multi-thread environment, which is also sad. So yeah, let's think about, do we really want to differentiate BLAS routines? I mean, Enzyme is cool because it is able to do that. It's the only AD tool out there, which we have for Julia, which can differentiate BLAS routines. But apparently, we might reconsider that, right? So let's try on a higher level set. So if you look at BLAS routines, actually, that's, for example, the matrix vector. It has like 12 different arguments, where on the JuliaLand you might have only 2 types, right? So differentiating defining gradients for 2 arguments is easy. For 12, it's not so much fun anymore. So maybe we want to go a level higher, right? Enzyme has its own set of custom derivatives, like you have a chain rule ecosystem. Enzyme is a bit specific. It wants its own enzyme rules. But at the end of the day, you can define it on a higher level in Julia itself, which is nice. So thanks to the Exon who went ahead and added some extra rules, that's the most simple function. Dot is literally like take 2 vectors, multiply and add them up. So how much faster can it be? Apparently a lot. So that already, it's the most simple function. Even there we kind of screwed up before performance-wise, so that shows how important those rules are. Obviously, now that we have Julia level rules, we are wondering can we go even better? Can we get some compiler internal rules which give us even better performance? Which is a route which took us a lot of time afterwards, because yes, we can write compiler internal rules. That's called TableGen. It's an LVM-based tooling which allows you to do code generation, which is great for such simple cases. For large functions, it's a trap, because you can define your custom derivatives, but like that's what you end up with. So it's still a lot better than whatever we had before, because if you try to actually write the code out by hand, which differentiates BLAS, like matrix-matrix multiplication, for example, it's over 1,000 lines of code. And BLAS doesn't only have one function, it has like 20, 30, and then you look at LAPACK and you're completely lost. So we do need some tooling. It is great, it's still not super readable, so there are unfortunately not that many people yet who contributed enzyme core AD rules, but it's at least making progress. The question now, was that really worth it? And yeah, I mean, one of the things which we see, if we actually stop replacing your optimized BLAS library with a single-threaded generic library, we do get multi-thread speedups, which is great. We do also get a couple of performance improvements over competitors. For example, in comparison to Cygod, I don't have numbers before. I think we are pretty slow. Now we are on average maybe like 2 times faster on a single-threaded version. The multi-thread version was a bit awkward while benchmarking, but those numbers are also pretty old, so hopefully we improved a bit since. But yeah, there are also correctness challenges, because first we want to test all of these rules, of course, in CI. Now, what do we do with, for example, QBLAS? It's just another BLAS library at the end of the day, but we don't always have an NVIDIA GPU in CI, right? Same with all those different libraries. There's OpenBLAS, there's Intel MKA, there are so many different variants. Some are written in C, some are written in Fortran, and even if you have a Fortran library, it might not behave the same as another Fortran library, because depending on your compiler, the ABIs are completely different. It's a mess. Writing manual tests is also not really sustainable, because on a high level, yes, you can test your Julia rules for BLAS routines, because you have 2 input arguments, right? How complex can it be? As you've seen on the lower level, BLAS routines actually have like 12, 15, maybe 20 input arguments. And each of those is, for example, transpose. So like, what if you flip one of your matrices? If you have a diagonal matrix, you have the upper diagonal, lower diagonal, what's triagonal, yeah. So they're just a combinatorial explosion of steps. We don't really want to write them by hand, because we tried that, we didn't go far. People complain about incorrect results, which obviously isn't great if you want people to use your tool, right? So what we did is we did some kind of symbolic testing. So we had fake versions of our BLAS calls. So our own implementation, which instead of computing any outputs or so, we don't care about outputs. We just had a kind of global stack. And so every time you call the BLAS routine, that BLAS routine pushed something on the stack saying like, hey, I'm a dot call, or I'm a matrix vector call. And I have those 12, 15, whatever arguments in that order. And then it's just getting saved. Now the funny thing is, if you differentiate such routines using Enzyme, Enzyme is going to recognize the name, because we match obviously whatever BLAS routines out there use as a naming convention. So Enzyme is going to introduce new BLAS calls, which then again, if you look at the implementation, are still fake implementations. So the derivatives which we implement will also push their name and their arguments onto a stack. So once we differentiate the function, a fake BLAS function, and we look at our stack after running, we see only like, hey, I'm a dot call, I'm a XP call, I'm a XP call, which is like scalar times vector. And yeah, so now we can check our inputs to each of those calls. We don't see the actual outputs, because those are a bit complex to test, but we can automate those types of testing. And we did catch a couple of bugs. Now we are able to test at least QBLAS also in CI. And yeah, that's obviously pretty nice. Let's see. Yeah, so what's our final performance? Oops, wrong slide, sorry. Yeah, so our linear algebra routines with Enzyme now have a couple of improvements. We have around 5,000 lines of logic, which we wrote in order to like automate all those code generation thingies. We have around 60, 70,000 lines of code. That's only for the first, let's say, 10, 12 functions. So we do hope once we add the remaining functions, the numbers of generated lines go a lot up without any of the logic having to change. And yeah, we do have a lot of features. For those, I mostly have to give a shout out to Billy, since I implemented the basic logic reverse mode and some testing, and he added like all those fancy new things. So for example, we now have runtime activity, which in Enzyme world means I'm at compile time not really sure if I want to have a gradient for that, so just be aware I might ask you later for it. It has a small runtime overhead, because we do need to cache a couple of things, but now that means later, like during runtime, you can say like, oh, actually, give me the gradient, in which case, yes, we give it to you, it has a small overhead. Well, you can also say, I don't need any gradients at runtime, which means, well, there won't be any gradient computations. It still has a small runtime overhead because we cache things in the forward pass, but it's pretty small compared to computing gradients at all. We do have batch mode as a new feature. I'm not sure about how many other tools are there which currently support that. I think it's a bit work in progress. We do have cuBLAS support. It's pretty new, so please feel free to test it. And yeah, the functions on the BLAS side, these are the ones which we support. So it's the basic ones like vector-vector product, scaling a vector by a scalar, matrix vector, sparse matrix vector, general matrix matrix. And the second line is a couple of solvers. So yeah, some decompositions. We do have our symbolic verification system, and thanks to an external contributor, we also have a couple of tests, like normal tests, to make sure that our symbolic verification system is also working. And yeah, so now that we have all those things, can we look a bit more into the performance? Like we've shown we are approximately 2 times faster than Zygote, right? But we've seen there were a couple of awkward drops around here. So what can we do? Asking our profiler. And there was some interesting insights if you look at the performance results, because generally if you have computations like matrix-matrix, you do expect that actually there's some work to be done. It's not only copying elements around, it's also like some pure math. But if you look at what VTune tells us here, approximately 70% is just a mem copy, which seems a bit awkward. So our assumption is that enzymes, despite being like already 2 times faster than Zygote, still has some internal bugs. Probably, maybe we got some bounds wrong or so. So we are caching more than necessary. So that's something we want to look into, because obviously if we can strip those 70% down to, let's say, 40 to make up some numbers, then we'd be even faster, right? Makes sense. Yeah. So that's a bit awkward. We also have some benchmarks against C, because I mean, Julia often enough claims to want to solve the two-language problem, right? So now that we have our compiler-based, table-gen-based rules, we can suddenly also support C, which we didn't have any fallback for C before. So Julia was in the past actually the only enzyme front-end which supported BLAS routines. Now with those rules, we also have C support and all other languages. And I mean, one thing we see is like first for the primal, which means the original function, which just is based on some, I think, matrix vector multiplications. Enzyme, like the primals are all pretty much the same. So Julia, C, whatever, it's close, right? Now, if you look at the results where we differentiate things, suddenly things become a bit worse for Julia. So Julia is for some reason slower, and once you look into the like matrix implementation, you also see why. So in CLand, everything is pretty simple. You call malloc, calloc, whatever, and you get some allocation. You have a pointer to it, and you pass those pointers to BLAS. It's a pain because you've seen like how many arguments you actually have. It's like 12 different ones. You'll never get them right. So you hopefully use some library like Eigen, which makes it a bit nicer. It's still a pain. On Julia instead, you have your nice objects, matrix objects, which like as your variable first is a pointer, but then your matrix is also a pointer, so you suddenly end up with a double pointer, which for enzyme is bad, because if you have a single pointer, we can observe, like, are you writing into your matrix? Are you overwriting some elements? Well, we might need to cache them, because for the reverse pass, we need the original input to compute correct gradients. So we might cache it. But if you have double pointers, that's kind of a lost game. So we don't know if you write into like your outer pointer, like where do those inner pointers point to? Do any of your matrices overlap? Do your vectors overlap? To some extent, that's allowed. So we need to be conservative, which in the worst case means if you have a like BLAS routine which has 5 input matrices and vectors and you overwrite one of them, we need to cache all 5, which is obviously terrible and which could to some extent explain why we are mem copying so much. And yeah.
Have you checked whether fixed size to arrays fixes this? Because that will fix that doesn't have the double pointer interaction.
Is that the memory-based one?
Yeah.
Yeah, we're waiting for that. As far as I know, last time I talked to Billy, we don't support 1.11-ish.
Okay.
So we are waiting, and yes, that's what we're going to do. Which is also why we didn't investigate on the enzyme side, because we hope the problem is going to solve itself. Yeah, so do you have any questions on like any of the performance aspects or any of the future development? No? So I have 2 more extra slides, but
okay.
Yeah.
Keep the questions up here.
Okay, yeah. So yeah, one project which I've been working on last year after implementing like some of those derivative rules are optimization. Because I like working on LLVM, as you might be able to tell, and LLVM has all those fancy optimization paths, right? The issue with that is they're pretty low level. Like I showed one example, which is loop invariant code motion. There are a lot more of these. They are pretty low level. So they don't really understand your math. Like if you have matrix objects, I mean, at the end of the day, for a compiler, it's just a pointer. Or in the case of Julia, it's a double pointer. It's not, there isn't really a concept of a matrix, unless you go for some higher level compilers like XLA, MLIR, whatever. They might be able to do it, not so much on LVM itself. So what I did is first, a simple one was BLAS GemV, which is matrix vector. Now if you have a couple of matrix vector products, and you do know all of your vectors are consecutive in memory, or at least they have the same distance to each other, then you can merge it. Because like the general matrix call literally has one thing which is called increment y, which says like, hey, how much space is there between your different columns of your second matrix? So you could merge them if you know a little bit about your inputs. And in the case of batch mode, we might do that in some cases. So technically, this one would be a lot faster, because I mean that's technically what's already happening for batch size of 4. We want to merge them. There are a few more of these optimizations, which, like if you have outer products, inner products, there are some cases where you don't need intermediate results. So just by matching on those names, you can recognize some of the intermediates being useless and just effectively throw away whatever BLAS combinations the user used and insert a smarter row of BLAS calls. This is something I worked on. I never really finished. Nowadays, we are also not 100% sure if that's the right approach, because first, there are some higher level optimizations. There are polyhedral optimizations, which have some understanding of math. And for example, if you look at the enzyme AD repository nowadays, there's Reactant, I think it's called, .jl, which tries also to compile everything through MLIR, which has already all the infrastructure. So we don't really need to rewrite all those optimization passes if we use MLIR instead of LVM. Yeah. Okay. Yeah.
Last one.
Sorry?
Is this the last slide?
Yeah.
Oh,
Yeah.
okay. Then
Yeah.
please thank our speaker first. Now we have a question round. So
Yes.
anybody has a question?
Yeah.
Maybe just a quick question about the, you just mentioned like the reactant and MLER story. I was wondering to what extent you were seeing like the future of enzyme, like going with for matrix operation, going to the MLER route or the optimization you're kind of discussing?
I mean, I'm not the one working on the MLIR side, so I only can give you second-hand information. But yeah, so for high-level optimizations, it's generally nice to have a higher-level dialect, which MLIR offers. So I do know they want to use it, I think, mostly for ML tools, because for ML you have all those large tensor objects. You don't really have like really nitty, like small math for loops or so. So that should be a lot faster. If you ask Valentin, he tried before to use MLIR in Julia. The issue is back then, it's called Brutus, I think. So what he did is effectively replace the LLVM backend of Julia and just insert an MLIR backend. The only issue is if you go for the Julia intermediate representation, that's already pretty low level. So at that point, you already lost your information, like, hey, that's a matrix object. So then you need to try to regenerate all that information. It takes a lot of compile time, and usually you don't really get much performance out of it. So now the new one, Reactant, starts pretty high level. I don't know, do you know more about it? Fair enough. But yeah, it starts pretty low, high level, so hopefully they get some more performance out of it. Yeah.
Any other questions? I have one question myself. So I wonder if you can just, given the talk yesterday from Jeff, if you already can think that whether this code can be fully statically compiled. Seems that you're still using some runtime niceties.
I mean, the runtime activity, you mean? That's not really something which should matter for the compilation process. It's just we have both paths available and we cache a little bit more, but it shouldn't hinder static compilation. I do know Enzyme has a pretty unique compilation pipeline in the Julia ecosystem because it's based on GPU-compiler.jl. I'm not so much of a Julia compilation expert. I mostly work on the backend, so I can't tell if there's anything which blocks pre-compilation, unfortunately.
Okay,
Yeah.
no, but if it works with that, maybe I'm pretty sure it
Yeah.
will go with static, but make sure that it will be statically compiled so that
Yeah.
other people can just deploy in HPC and other.
Yeah, that would be pretty nice, of course.
Okay.
Yes.
Do you have more question? Another question?
So from the Julia compiler side, I think Valentin's talk on making GPU compiler precompilable with specialized caching, I think should mean that as of whenever Enzyme gets Julia 1.11, I think, maybe 1.12, somewhere in there support, it should become precompilable and therefore statically compilable eventually, but do not take this as gospel.
Okay.
Okay, thanks for that remark.
Okay, so we get all the nice things at one, like our memory types and the pre-compilation, hopefully.
Yeah, hopefully.
So yeah, then in that case, we just need to wait a little longer.
Okay. Oh, that sounds great. Okay, more questions? If not, then I would like to thank our speaker. Yes.
So there's a package that Gabriel.
Is there the connection for adapter for the mic?
Oh, this one is here.
Oh yeah.
Just take this one.
Okay. I wasn't sure I was allowed to.
You are allowed.
Good.
I give you permission.
Excellent. The permission is good to have.
That's good. We're fine. No, 5 minutes ahead. Thank Nicola.
Does this work?
Yeah. Like, if you like fixed size array packaging is actually a pretty simple package. So like,
Yes, please do.
Yes, sure. Oh shit, this is not the. Oh yes, it's on the side.
Oh, that.
It's on the side here.
Ah, I wasn't.
There you go. And the other side.
yeah, it should have all black ones already, I think. Not sure. Yeah, it would be interesting to test out whether and how well it works, because
We good? Yes, we have video. Okay, good. Okay. While our speaker finishes setting up, please move to the next talk, or if you want to stay here, you can keep the discussions outside, please. Okay. Well, while our speaker finishes setting things up, I would like to thank Domenico. We know him from TU Delft, right? So I know that he works on the finite element method, and we had another talk before in the local meetup. So I'm very happy to have you here. So without further ado, please, you have your microphone, right? It's over there. Just make sure that you speak to the microphone.
Excellent.
Round of applause.
Welcome. Thank you very much for being here. My name is Domenico Lahey. However, there is an issue with the screen, so let us first try to fix that one.
You have to mirror, right? Or
Yeah, exactly.
I don't know how to use Mac.
Best way you can avoid it, you can do is compare the text files, and I'm not satisfied with that.
Do you have usually there's a mirror button.
Should just be a button somewhere. It's, yeah, I think if you do that one there. Yeah.
There you go. Thank you. You only know the Linux, that's it.
Thank you very much for the audience, for helping out, for the hardware. Prior to going to the content, I want to tell you who I am by showing you where I live. So this is a picture of my apartment block where I live. This was built in the 60s, early early 60s, late 50s. And obviously the picture was taken on a sunny day, unlike today. And I will show you also the environment of this apartment block by showing you the distribution substation that supplies electrical power to my apartment block. The substation is about the same age as the apartment block. Obviously, when people move in, they need to have power to live there. So the left part of the picture is old, dated. What you see on the right is new. What is there is a loading station for an electrical vehicle. And that's there for less than a year now. And the issue is that when the house was built, obviously people didn't have in mind that it would be later on also the loading stations for electrical vehicles. So there might be a mismatch between the design of the distribution subblock of actually how it's being operated nowadays. The problem is a bit more universal. Here you have a newspaper clipping of how the power supply system is ever more being stressed in its operation. This is a problem that not only exists in the Netherlands, but also globally, also more worldwide. So how does this congestion system affect the distribution of power on a low voltage level? We have to do or to deal with new loads, for instance, electrical vehicle charging, new infeeds, for instance, by wind farms or by solar cells or by local storage. We have the hardware of the past that were built having the old specs in mind. And there's therefore a need for new simulation tools to be able to design and operate the existing hardware. And this is what the project aims at doing. And we target here the low voltage low voltage power transformers. What is a low voltage transformer? In the primary side, and you have a winding that requires the power. This is the load side. It is typically a low voltage winding. What you see here is a design with one phase. Typically, the system works with 3 phases. And you might have also more complex designs of the ferromagnetic yoke. But this what I show you here is the most basic design. What I want to do in my modeling approach is to explain how the power transformation works. So what I do is I make a model of the Maxwell's equations, most simplest form. So I introduce here the magnetic field and magnetic flux. To be able to solve that mathematically, I introduce the notion of a potential, and finally I arrive at a diffusion equation for the potential for the field. And my scope is to be able to solve this in a mathematical model, be able to later post-process for the losses generated in the windings in the core, to be able to subsequently be able to model the heat loss in the device. What you see here is a simplification. I left out all kinds of naughty details because obviously the field will vary in time, particular frequency, and you have variation in field. You also have electrical effects to take into account. Thermal management might be complex to deal with. There's the need to do the cooling of the device by oil in the transformer block or by ventilating the substation. And obviously we want to be able to see how the model performs, maybe also improve it by making a digital twin of the model and be able to use local information on the weather, for instance, to be able to improve the model. So what I saw before is simplification. In reality, obviously, I'm wiping things under the carpet in a first analysis. Now, this is a conference on Julia. Obviously, we want to solve the model in Julia. So one might say there are already excellent finite element solvers around. The GitHub and Ferrite are two examples, so why not just use those? I wanted to deviate from that path, be able to harvest on the entire Julia ecosystem, enough for everything that we have to be able to solve the problem. And I do this in collaboration with Staden, which is local DSO in my area. So this is maybe the most important slide of the talk. What I show here is the structure of the course that I teach using Julia with the design problem as motivation. The course has now 3 blocks. Block 1 of introduction, where I do 1D and 2D models in a simplified setting. Then I do a finite element variation formulation to be able to treat non-uniform meshes. And then I do the application. I try to apply the finite element method to be able to solve the potential equation for the magnetic field. And this is a course that spans 7 weeks. Roughly, the course is followed by 20 to 25 students at the master level. And the course material also serves me to bring the Julia also to other teaching that I do at the university. So what do I do in block 1, just to give you more specs of how the course has been designed. I do first the analysis in 1 dimension, because in 1 dimension things are easy to develop in the first instance. So I solve the Poisson equation in 1 spatial variable. I'm still thinking about a name for the package. So maybe something with fish inside it might be appropriate, maybe Flemish fish, given also my Flemish background. What you see here is the problem without time. If you can do the time-independent case, later on you want to do the time-varying case as well, and maybe also the time harmonic formulation. And I have examples in the course that allow us to do this. Okay, once we can do 1D, we can also try to move to 2D. What you see here is a cross-section of the transformer that has a middle leg and 2 side legs. And around these legs, the windings are being applied. Please remember that the configuration has a middle leg. This will be important for the future of the talk. On this mesh, so we have here a set of elements forming the mesh. On this mesh, we want to construct the discrete problem. So therefore, the matrix and the vector, by doing a loop over the elements. So therefore, doing a global assembly by looping over the elements individually. And we needed some time to figure out how to do this in a stable manner, but now we have arrived at it. We are trying to further explore the assembly part of the code by looking at issues as lazy objects or using it as a map to be able to arrive maybe at a more readable implementation. I'm happy to have feedback on that. The use of AD tools discussed in the previous talk to be able also to do optimization and to treat nonlinear materials. How to make the code to be more generic, working for 1 and 2D, or maybe also working for different orders of the implementation. And doing a parallel implementation either in shared memory or distributed memory. These are interests that I would have to be able to speed up the model and bring the model to a digital twin environment. We have also issues on the linear solve, looking at issues as comparison between direct and iterative solution methods, and using legacy code such as the PETSI library to be able to accelerate the code overall. I will now show some sample results of what we are currently able to do. What you see here is the computed magnetic flux in the configuration you saw earlier. So here we see a snapshot of how the field distributes in the geometry. And what you see next is a more detailed analysis of what happens in the central leg of the transformer. One issue is the fact that with these new devices, we expect to see higher frequencies in excitation. And what they're trying to simulate here is the effect of the higher frequencies on the operation of the device. So the picture shows a left and right subfigure. The left is what happens if we simplify the model to have a linear magnetic behavior, and therefore we have a given flux distribution in the core leg over time, and this looks fine. If we switch from left to right, we will see that we see two effects. The fact that the flux is lowered, this is the saturation effect, but also there is a shaving off of the peaks. So if you shave off the peak going from left to right, what will happen in a frequency domain is the occurrence of higher frequencies. So what I show in the picture over here is again a comparison of linear left with nonlinear right, and the fact that due to higher operating frequencies, also the frequency in the flux distribution increases. What this means is that in the transformer, you might have higher losses, and therefore locally you have an increase of peak temperature, and this might be damaging for the whole device. And therefore the interest to be able to capture these peaks in a realistic fashion. Okay. To conclude, I talked to you about a problem in industry, that is how to model transformers in a distribution network. How I take this problem in an educational setting, in a course on the finite element method, and how this dialogue between industry and students is shaping the course overall, and how we're able to bring in Julia in an environment that encompasses both industrial research and education. And I'm happy to receive feedback on how to improve the code further. Thank you very much.
Now we have plenty of time for questions. So.
Thanks for your talk. I'm delighted to hear you use Julia for educational purposes.
Okay.
I wish I've been a student. This was around, I think, 25 plus years ago when I took these kind of courses. My question is, if you do this finite element kind of work, the whole secret is also about the gridding. You know, you need to have fine grid where a lot of changes are ongoing. You can do with a coarser grid. So what are you using for gridding here?
Thank you very much for your question and your feedback. It's indeed sad that at times the academic settings is slow to evolve, let me put it that way. You mentioned the issue of how to do the mesh generation. If you, what you see is that due to the higher frequencies, you have locally strong gradients in the flux that need to be resolved well. Therefore, if you look very carefully into what we did over here, this mesh was not generated by coincidence. We know a priori from analytical computations where the flux will concentrate, for instance, at the sides of the core lake due to skin effects, and therefore do there a priori a local mesh refinement. So this is already taken into account in the simulations.
What did you use to generate this mesh? Because this is also an adaptive mesh with quads and...
This is generated using Gmesh.
Gmesh, okay.
Yes.
Nice.
But then it's manually generated by the knowledge of the person.
Exactly, yes, true. This is done because obviously these computations have been done before. We're not the first ones to do this, so we kind of expect issues to appear and take the precautions. That's true. In a more evolved version of this, you would like to be able to discover where the flux will concentrate and do adaptive mesh refinement. And this is on the to-do list for future the code developments. For instance, the ferrite people who are also here are looking into adaptive mesh generation in their implementation. I don't know whether the Trixie people are doing the same. They're at the back. We can discuss with them. So, but it is indeed a very relevant issue to point out.
Okay. Another question?
Yeah, thank you for the talk. It's awesome to see finite elements showing up. I'm a bit curious about your software choices. So you mentioned in the beginning that you decided not to use the finite element frameworks that we have available in the language. Was that a choice for pedagogic reasons? And what do you do in the course? Do you have the students write like everything from scratch? Is it a somewhat specialized code for what you're doing then, or why did you make that choice?
Thank you very much for your questions. These are relevant questions to answer. The choice to stay away from prepackaged stuff is to be able also to expose what really goes on to the students, right? So I I deliberately build up stuff step by step. And I also take time in block 1 in the lab sessions to teach them how to use Julia. And you're starting, because Julia is new, right? The bulk of the education still relies on non-Julia tools. So also we want to take time to introduce Julia in the lab sessions. And block 1 allows space for that. I tried to use the Trixie code in the master course in April. And I discovered that students have a hard time digesting Julia. They see type definitions, they don't know what they mean. So if I start immediately from day 1 with Trixie or with Ferrite or with GitHub, the students are confused because they need guidance into the language of Julia. So that's what motivates doing it in a step-by-step way.
Yeah, thanks again for the talk. I was wondering, is there something that conceptually holds you behind doing unsteady simulations? So because, I mean, OrdinFAQ makes it super easy to like just, you know, formulate your FEM model like as a function. You need initial condition and you send it over to ODE-DFAQ.
There is indeed a good suggestion, and what I show here is indeed the time-independent situation, but I also do the time-variant case as well in the lab sessions.
Ah, cool. But are you then also implementing like your own ODE solver, or how are you doing this?
Not yet. We are relying on the tools that DFAQ does provide to do the time varying case. However, in reality, the transient case is difficult because we also have to take into account the algebraic constraints coming from the circuit. So we also have to have the DAE solvers to be able to do the transient simulations.
Okay, thank you.
I could see you talking about solving the coupled problem. I was curious, are you solving the thermal model directly on the grid as well as the EM in concert? Are you doing that together?
Not at the moment. At the moment, we are cheating for educational purposes. It is, we solve what you see here 2 times in a row. We do first U being potential for the field, post-process, arrive at sources for heat, and then do it again where U is a temperature.
Okay, so just a one-to-one.
Yeah, exactly.
Okay.
However, obviously, we are aware of more complex approaches, obviously.
Yeah, thank you.
More question?
Yes, so you mentioned that you have these higher frequencies, higher harmonics occurring at magnetic saturation.
Yes.
Under which condition does this magnetic saturation occur?
Excuse me?
Under which conditions does this magnetic saturation occur? Is it like if I use this transformer at higher energies or higher?
Yes, true. The question is about when does saturation happen. So the coils are wound around a core of iron, and that iron has its physical properties. You can compare it to a sponge. A sponge that absorbs the water. However, if the sponge is wet, if the sponge is fully soaked, it doesn't absorb the water anymore. Same as here, right? If you saturate the material with magnetic flux, at a certain point it will no longer be able to take it up, and therefore there will be a fringing flux through the air.
Thank you for the talk. Are you modelling eddy currents as well in the simulation as part of that? And are you, I was thinking particularly in reference to the higher frequency components, are you including the skin effect?
Yes, we are. Yes.
Okay.
I have one question myself.
Okay.
So since you are using this to teach Julia, thank you very much for that. I wonder what's the usual struggles that students have by learning Julia, the language.
Okay. Okay. I can tell you the good news first. When I introduce Julia in a teaching, students are happy to go along with that. They don't complain about it. And I teach now different courses using Julia. In the course that I show here, there is a place to introduce Julia. Right? There is a first lab session of 4 hours. There's lots of documentation. There's Jupyter notebooks. They can go play around and you learn stuff as they go, which is wonderful. That's fine. That works. What doesn't work is at the master level, giving a project-based assignment on simulation and modeling, hoping that they will learn Julia from the out of the blue. We need to give them more guidance. And what I encounter there is, as a struggle, is the fact that Julia is a typed language, and students don't know anymore what the typed language is. They come from Python, they come from MATLAB. Why do you define types? That's one struggle.
So types is usually the main problem.
Yes.
Okay.
At least in my experience.
Okay. Something else, maybe documentation, maybe.
Documentation, yes, but that's a bit universally, I think. But there I try to compensate by writing bits on my own. Okay. How do you use Gmesh? Okay, fine. We managed to generate the mesh. Mm-hmm. Wonderful. After efforts, installing it, making it run, good, finally are here. Then comes the issue of how to do a traversal over the mesh elements. And obviously, if you know Gmesh for ages, you do it fine, but for students, it's new.
Okay. Okay. Yeah. Okay. I can see that. Okay. Thank you very much. So I think that we should just thank our speaker, and we will have a short break, a 10-minute break, maybe a little bit longer now, 12, and we will reconvene here. If you want to keep it here. I'm on now? Okay. So I think we should just get started, otherwise we're not going to make it on time. So I want to thank our speaker, Nikolai. So he comes from Denmark, so kind of a neighbor. And we just found out that his package, the one he's going to present right now, initially I started at your PhD studies. Your studies, university studies, but I usually say like, oh, well, after the university, students just leave their packages and to rot, but he keeps alive, so I'm very happy with that. So please welcome our speaker, and he's going to talk about his package.
Thanks a lot for coming, and I would like to talk about my package called Ray Trace Heat Transfer, which models 2D enclosure radiative heat transfer, and the slides you can see on this link if you have your computer. And yeah, this is the agenda. What I'm going to talk about, I've structured it as a series of questions. First, I will talk about what is this package for, and why this package, and then what does it solve. Which limitations does it have? How does the meshing work? How does ray tracing work? How does the heat transfer calculation work? And the future of this package. And then just the last slide about why I used Julia for this. And these two pictures were generated with the package. It's generally where you can see that the top picture is there's some random noise because I only ray traced a few rays, and in the last picture there's much more coherence, or what to say. Then what is ray trace heat transfer? The JL4. It is for it's a Julia package for 2D radiative heat transfer calculations in participating media in custom geometries. And then I want to define what some of these terms mean, because it might not be obvious to everybody what it means. What is radiation in this situation? It is electromagnetic waves, or you can also see it as photons. And that's mainly what I do in this package. Then what is heat transfer? Heat transfer is net exchange of energy due to a temperature difference. Then what is a participating medium? A participating medium is a substance between two walls, for example, that exchange energy through radiation. And then this participating medium, it interferes with that, and that's in the image there. It's the participating medium that I have graphed, and a hot lower wall, and a cold top and side walls. Then the temperature distribution becomes like that. And my package can make custom geometries, and it doesn't have to be like squares. You can have skewed things also. But why radiative ray trace heat transfer.jl? It is relevant to, for example, combustion. That was my original motivation. But it is also relevant to climate sciences and astrophysics, where you also have some kind of gases that absorb and emit and scatter the radiation. So that's, yeah. Then what does ray trace heat transfer.jl solve? It solves the radiative transfer equation. I didn't show the equation here because it's a long integral differential equation, and then I had to explain all the terms. I would rather explain the phenomenon that it models, and it's an energy balance along a line of sight in any domain. Then we have some incident radiation and some transmitted radiation, And this equation models on a differential level what happens to the ray from it goes into that differential volume to it goes out. So then you have to integrate it along the ray. But the thing that makes it complicated is that all possible paths for the rays, they are coupled. So that's why it's an integral equation. And it's incredibly hard to solve, at least for general domains. And some limitations of my package. It cannot yet solve 3D problems, but I have some ideas on how to do that. It cannot solve the full spectrum, and it has some limitations due to the matrix formulations that it uses. The size of the matrices, they basically scale with the n square of the number of elements in your domain, so they can become very large. I'm thinking about using memory mapping to have the matrices on the disk and then allowing for larger matrices, but I'm looking into that. It's also not yet implemented for the GPU. Then how does it work? The package, first we mesh, and we build it from we build it like modularly, where we build it from convex quadrilaterals, and we just build one at a time, and then we plot it and then add another one, and each time we specify if the boundaries are solid, if they are impenetrable, or if they are open. So we can actually build something like a very complex domain from these definitions. And the reason they have to be convex is that then they are easy to ray trace. And then we generate the mesh by specifying the number of splits in each direction. And as I said, they can also be skewed in any way, basically. And then I showed here some ray tracing. I know it looks very chaotic, but it's a single function that samples and traces the entire geometry. And then the results of the ray tracing, they are stored in matrices, where each row in the matrix describes the probability from emitter I, from radiation emitted from emitter I, going to column J. So that's why we have for each row we have J elements, where one for each element in the domain. And in this picture, I think I traced what? Okay, I traced 2 per emitter, and in general I trace millions to get accurate results. Then lastly, the heat transfer works by using the matrices to do heat transfer calculations. Some things that I want to add to the package is a new matrix method, 3D domains, GPU-based ray tracing, spectral support, non-uniform gas properties, and time-dependent problems. And then lastly, why do I use Julia for this? Because this is my ray tracing. This is just pseudocode that I wrote to simplify it. But as you can see, there's a parallel for loop, then there are 3 nested while loops. And this is basically what models it. So it needs to be very fast, especially if you have to trace 100 million rays or a billion. But in general, intuitive syntax, great packages, excellent linear algebra. And for ray tracing, it's important with the fine-grained control, excellent speed, and parallel programming. Yeah, thank you for listening.
Yeah, I think we had time for like 2 questions. So. Okay. Yep.
Thank you very much for a wonderful talk. You mentioned that you use convexity to simplify the ray tracing.
Yeah.
Why is that? Can you do also non-convex domains, or what is required in your current implementation to do also non-convex domains? How much code will require to also be able to treat more general geometries? Thank you very much.
Yeah, thank you for your question. I can easily do non-convex domains. I just have each element in the total domain has to be convex, because when it's convex, I can do like for these. They have like 4 sides. In general, I ray trace in each. I call them sub-enclosures. I ray trace each sub-enclosure. It only has like 4 sides, so I have to do like a function that calculates along a line which wall do we hit if we go along this line, and then I calculate if we go a certain distance, did we hit the line? And then actually when I ray trace only on the coarse domain, so to say, and then I find out if there's an interaction point where I basically map that to the fine domain. But I can easily do non-convex domains. Yeah.
Okay. In the time, I think we have to wrap up. But
Yeah.
once more, we thank our speaker. So, next talk is just the results from the Julia survey, right?
That's right.
So yeah, I don't think I need to introduce more than that, except to thank you, Andrew, from Julia Hub,
you.
right?
Yes.
Okay,
Great.
please thank our speaker to present all these nice results.
Thanks so much. So this was the 6th annual user and developer survey that we conducted this year. So this year we had a shorter field period than we've had at sometimes in the past, and so we ended up with 682 interviews, which is a smaller response rate than we've gotten in the past when we had a longer fielding period, but still a good representation. The demographics of respondents this year are similar to the demographics in previous years. So we have, we still think we're getting a select subset of Julia users and developers. We're getting the people who are most engaged, who are most involved, who are choosing to respond to the survey. But we're getting pretty good representation across professional and academic users, across industries, across countries, languages, etc. So we recruit respondents into the survey using as many different platforms as we can. We advertise on Discourse, on the JuliaCon website, on the Julia Lang website, Julia Hub channels. We put it out via our X and LinkedIn channels. We send emails, etc. Everyone who gets the Julia Hub monthly newsletter got an invite, and so on. Many of the questions that we ask are the same from year to year, so you'll see tracking data from previous years for the purpose of comparison. Some of them are different. We're seeing a continuing increase in those who are saying they're using Julia more and more. So 95% say that they now say that they have used Julia regularly or frequently during the past year. And numbers for most other languages are down over the previous 3 years, with the important exception, which we'll see in a few other places as well, of Rust. So even among people who use Julia, we're seeing growth for Rust. We also asked, which of the following languages have you used, do you plan to use regularly or frequently during the next year? So the bar on the left, the past year, is the same data from the previous slide for comparison. And then next year is what do you think you're going to be using during the next year? And so, continued very high numbers for Julia. Julia users and developers expect to be using less and less of most other languages, even as they're using Julia more and more, again, with the exception of Rust. And that's something we saw last year for Rust as well. 84% say that Julia is one of their favorite languages. That's the highest we've seen in this survey, and we've been asking this question for 6 years. And again, other languages continue to decline. And then 96% total say either it's one of their favorite languages, which is 84%, or 12% who say that they like Julia. So people who use Julia becoming more and more favorable towards the language, like it more and more as the language continues to develop, as there are more packages, as it becomes easier to use, as well as they get better using and programming in Julia. Thinking only about the technical aspects or features of Julia, what are the technical aspects or features that you like most about Julia? And then you can see with the asterisks at the bottom which options were added and when they were added. So that's why you don't see 6 bars for each of these. But the number one continues to be speed and performance, followed by the package manager, followed by ease of use, open source, multiple dispatch, composable, ease of installation, solves the 2-language problem, type system, etc. Thinking about the non-technical aspects or features of Julia, what are the non-technical aspects or features you like most? Number one continues to be free. You don't have to pay to use it. Number 2, the community of developers is talented and active. Number 3, the community of developers is warm and welcoming. Easy to create packages. That number has increased significantly in the past year. MIT license, easy to get help and information online, great documentation, easy to contribute to the language, lots of great teaching and learning resources available online. The biggest technical problems with Julia, number 1, cannot generate self-contained binaries or libraries such as .exe, DLL, etc. That has increased over the past 2 years. Slow compile times, too long to generate the first plot, confusing or overly verbose error messages. I require packages, libraries, or tools that are only available or are more complete in another language, etc. The debugger is too slow and or not fully featured, and so on. The biggest non-technical problem, there are not enough Julia users in my field or industry, followed by online tutorials and documentation that are outdated. My company, university, clients, or other organizations I work with do not allow or support Julia. Why did you start using Julia? Number 1 is elegance of Julia. Number 2, Julia seems like the language of the future, faster for the work I'm doing, preferable syntax to other languages, solves the 2-language problem. Where do you interact with the Julia community? Number 1 is discourse, and that's grown significantly over the past couple of years. GitHub has also grown. Slack is up. Less on YouTube, more on Zulip, less on Stack Overflow, more on Discord, less on Twitter, Reddit, and less on Julia Forum. Which of the following best describes your use of Julia? Number 1, I use Julia for research, individual work. Decline in those who say they use it for hobby programming. I use Julia for development as part of a team. That's a significant increase. I use Julia for teaching, and I use Julia in production for a business critical task. Which of the following types of Julia packages have you created or contributed to? So significant increase in those who have created or contributed to open source packages, both those that are registered and not registered, as well as an increase in those who say that they have created or contributed to packages that are private and not registered in a private registry. In which of the following capacities do you contribute to Julia? More say that they are writing Julia as a component of paid work or that part of their work is paid. Fewer say that it's completely voluntary. How many volunteer hours do you spend working on open source projects? So we're seeing that the largest numbers say that they're spending 1 to 10 hours per week. When did you first start using Julia? Most Julia users and developers who participate in the survey have been using Julia for the last 2 to 6 years. What percentage of the programming work you do is in Julia? For the first time, more than 60% of respondents, more than half of respondents say that at least 60% of the programming work they do is in Julia. So we're seeing a big increase in those who say it's 80 to 100% of their work, also in the percentage who say it's 60 to 79% of their work, and a decline in those who say that they're doing less of their programming work in Julia. How robust? Somewhat robust is the largest share, 62%. Which editors or IDEs do you use frequently? Number 1 is VS Code, followed by Pluto, and then further down Jupyter, JupyterLab, etc. What types of AI assistants do you use frequently? So we've been seeing a significant increase in use of AI. We've gone from 32% who say they use some form of AI to 48% saying they use some form of AI. And then what cloud solutions do you use? Again, we're seeing a decrease in the number who say none, and an increase in those using various cloud providers. How helpful and collaborative is the Julia community? The vast majority say very or somewhat. Plans to attend JuliaCon. Julia Up has really taken over in the past year and 2 years as the way that most people now are downloading and installing Julia. The most common operating system, Linux x86, followed by Windows, followed by Mac. Which kind of parallelism do you use? Number 1, Julia multi-threading, followed by GPUs, etc. NVIDIA GPUs are the most common accelerators. So again, we have more than half now saying that they use some form of accelerators with Julia. What resources have you found most useful? Number 1, the Julia manual, followed by JuliaCon presentations, YouTube tutorials, Julia books. Which of the following do you use? Sorry. So number 1 is data science, modeling and simulation, visualization, statistics. But as you go down, you can see, we've got scripting, differential equations, graphics, etc. Good representation across a variety of different areas. About just under half of respondents are professionals, and just more than half are academics. People can be both. They can be professional and academic users, or hobbyists and academics, or hobbyists and professionals. These are some of the titles that academics have. The fields that are most common among academics: physics, math, computer science, biology, stats, economics, geosciences, etc. But as you go down, you see medicine and health, aerospace engineering, sociology, finance, political science, climate science, astronomy, chemistry, etc. And then among professionals, primary industry, number 1 is software IT, and followed by engineering. But again, also as you look down, we've got people in manufacturing, agriculture, energy, automotive, logistics, etc. Well, no, this is... what type of improvements to Julia would make you more likely to recommend Julia to others? So number 1 is reduced startup time to first X, followed by more machine learning functionality, more stats functionality, more web development functionality. How many years of coding experience do you have? The biggest number, say 6 to 10, followed by 11 to 15. So the biggest number, 6 to 20. Yep. Great. So this will be available online, of course, and if anyone has any questions, please let me know. Happy to discuss. Thank you very much.
So thanks, Andrew. Well, I think we were just, when was it, yesterday or the day before yesterday? No, yeah, before yesterday we have a keynote, so I think this is a follow-up on that, right?
Yes, it is.
Or more in-depth explanation, I guess?
Yes,
on one of the packages, indeed.
Okay, one of packages. Okay. Let's give you a few seconds to. I think that we'll have to cut up. We'll dent a little bit on the break time, but I think it's fine, right?
Yeah,
if you need to
perfect.
go and run for your sandwich, please. I think we'll be fine today. So.
I'm gonna sit because I will do a bit of Pluto notebook. So is that good for the sound? Good. Right. Am I ready to go?
You're good to go.
Good. All right.
Just the frame a little bit.
Sorry?
You're a bit low on the cap in the video, but just the frame.
Okay, fine. All right, so yeah, hi everyone. Thanks for coming here. So I will basically follow up a bit on the keynote and just talk about what happened in the FTK, the density functional theory package that I mentioned at this lower left level of this basically high accuracy quantum chemical simulation. And in particular, what I want to talk about is some of the things we did on the direction of algorithms and the direction of error control, and also basically trying to combine communities. And I will show you a little bit how to actually use the code in practice. So I think from the motivation, I'm just showing this as a reminder slide to get it all back in your brains, in the active part of your brains. We need new materials, because materials is basically what limits the solutions we have to problems like climate change, energy, and so on. So as Rachel has pointed out on Wednesday, what we're doing is we're actually running quite a bit of computations. We're really simulating, for example, how such a silicon crystal behaves from the quantum mechanical point of view in order to understand, is it useful for solar cells? Is it useful for other technical applications? And as we have pointed out, this is something that we don't just do 10 calculations on. Really, we're more doing a few thousand, maybe tens of thousands of calculations. We're really like, for example, on this Archer 2 figure that we also had on our previous presentation, we really occupy something like 50% of standard academic computers with these kind of simulations, right? So this is stuff that people really do, and this is things where, certain questions now pop up that haven't really been part of this field beforehand. So just to give you some ideas, in particular, it's a question of complexity. So we started looking into this a little bit in the keynote. There's really a lot of different steps that one has to go through. First, generate the data, train some surrogates, for example. And basically, all of these steps have really a lot of parameters, right? So we're talking about things like tolerances, which algorithms do you actually choose in order to really run the simulation, which model, and basically all of these choices need to be made automatically now that we're running tens of thousands of calculations. And if I make a wrong choice, then potentially I get a wrong answer. So this is actually a non-trivial problem, and this is why people have developed actually these kind of workflow engines that I show here at the top that automate using heuristic choices the setup of these kind of simulations. But of course, this is not perfect, and in particular at the level of really running tens of thousands, hundreds of thousands of simulations, sometimes these heuristical setups go wrong. And then simulations basically need to be repeated. Again, typically this is done heuristically, but the key point I want to get across is every simulation that you have to repeat is wasting resources, and supercomputing is also not cheap, right, in terms of energy and of course also, therefore, from the climate point of view, it has an imprint. And humans typically do this checking, not always, but oftentimes. So basically, it often is in these workflows now the human factor that limits the overall throughput. So if we can make simulations effectively more autark, we can make them more robust and more efficient, we're saving not only on energy, but we also make it faster to develop and discover new materials. So our mathematical questions, so to speak, are how do we optimize properties, how much accuracy do we need, and can we use tools such as algorithmic differentiation to go through these things faster? Okay, and here this is just the math slide, right? So don't look at all the details and get scared. The key point to get across is that in this kind of density functional theory simulation that I'm running, that we are running in our code, we have a complicated minimization problem. So we basically minimize some energy functional over actually, it turns out, a Riemannian manifold. So this is not even Euclidean space. So we have basically a manifold optimization problem, nonlinear, non-convex, right? So basically, it's a complicated problem. That's what I want to try to say. And now just to give you the idea of what are the kind of research questions we're interested in, I'm actually going to focus on a slightly simpler model problem. And so the typical numerical analysis point of view, when you have such a minimization problem, what you're interested in is, for example, you want to come up with like fixed point methods. So in DFT, that would be the so-called self-consistent field approach. Maybe some of you know this. And there, what the key point is that the convergence of this guy actually depends on the second derivative of the energy, effectively. Now, other things that people are interested in is properties in response. So I will talk about this a bit more, but the point is that this connects to physics. And in order to do that, it actually turns out that, again, the gradient of the energy and the second derivative of the energy pop up. And similarly, in fact, if I want to do numerical analysis and I want to understand what is the discretization error, for example, in my computation, then again, the same structure pops up. So I have to invert a second derivative of the energy and multiply it with the first derivative of the energy, right? So the key point to get across here is that this energy functional, its first and second derivative, these are like the key ingredients to the kind of simulation software from a mathematical point of view that I need to understand. Okay? So that's sort of the mathematical structure. Now let's talk a bit about actually getting this to work in the context of a real quantum chemical simulation. The problem is that there's a clash of many aspects, such as community, conventions, language barriers, and so on, right? So I used here a very mathematical language. That's not something that is extremely familiar to people who come more from the application side. And in particular, in the applications, if you spend, like you do in math, basically a year or a year and a half on a paper, that's not going to work on a collaboration, right? Because people who do simulations want to be much faster. So therefore, we have basically problems that are social problems that cement in software, right? Because how you think about your research affects how you write your software. And in the end, as a result of this, these kind of mathematical structures that I have just alluded to, they're really not that exposed in existing codes. And however, on the other hand, mathematical codes that do expose the structure, they tend to be really slow and don't work so well in practical context. And here, same as I said in the keynote, I think if we can come up with software that allows these different viewpoints to compose in one code, that actually allows us to actually also compose these different fields and come up with joint academic research. And that's really been ultimately the motivation for the density functional toolkit, to make something that is accessible to different communities, to be able to treat like really model problems that are interesting from a math point of view, but also to go to something like 1,000 electrons, that's like a realistic scale system, and all of this in something like 8,000 lines of code, which is really, really small compared to what standard codes in the fields have. More recently, we integrated also, or start to integrate into high throughput. So the plan is that maybe over the next half a year or so, we are actually able to use our code really to run tens of thousands simulation on one of these existing state-of-the-art frameworks. We do standard integration with Julia things are listed here. And in the end, there's really been, I mean, to sort of prove the point here, that we have really a number of contributors from different fields on GitHub that contributed features, and some undergrads that did various kinds of work and really managed to push the state of the art of the code. All right, so some things that we did in research from a research point of view. So for example, we looked exactly at this gradient is equal to 0 problem, the self-consistent field problem. And the point there is that the parameters to choose is, in your iterative scheme, what is this p-1, the so-called preconditioner that accelerates your convergence? What's the step size, this alpha? And basically, this is exactly what these kind of parameters that are typically chosen by trial and error. However, now what we have come up with based on some mathematical insight is essentially algorithms that automatically look at the system that you have and basically based on the information you acquire while you're running the simulation, chooses automatically this preconditioning step in a system adapted way, such that we overall are able to perform much faster algorithms than state-of-the-art codes. So maybe our code is not as fast as state-of-the-art. However, we, for example, here win a factor of 2 just by being smarter about the way we solve the problem. Similarly, here we have a setup that automatically determines the stamping factor, which in existing codes is often something where people really need to fiddle around until they find the right damping for systems to work. And we can actually determine this automatically using a mathematically proven algorithm. Similarly, things we looked at in more recent times is look at properties. So energies are great, but in the end, it's really the change of the energy when you change an external parameter that essentially probes experimental quantities of interest. And here, when you look at this from sort of the algorithmic point of view, what it is at this self-consistent field, so this sort of gradient equal to 0 problem, that gives you a so-called fixed point. And then if you want to understand how this fixed point changes when you change the external parameters, so when you perform an experiment, this then leads to an implicit function, and therefore you can use AD, implicit function theorem, to compute these things. And that's exactly what we're doing, and the type of properties you can get with this framework is, you know, more or less standard properties of the field, forces, dipole moment, elasticity, spectra, various things like this. So this is things people are actually interested in practice. The nice thing about basically doing this with an AD framework is that you can also compute other derivatives, so things that are usually not so available, such as sensitivities or surrogates. And just to give you one other idea how we use AD in practice, here that's a quantity called the stress. That's something where you also need to compute a derivative of the energy, in this case with respect to the lattice setup. And here it's the code, and here, sorry, this is the code and this is the equation. And you see it's very much one-to-one. And I'm not actually cheating here, so if you want to take a look, this link here brings you to the code that we have live, and you will see it's basically this plus a bit of sugar around it. So this is how we do the computation. We really implement the physics. And just to give you an idea, that's 20 lines for us. Other established codes use something like 1,700 lines, simply because they hand optimize and hand implement these derivatives where we use AD. That's something that Niklas, who has fortunately joined my group a few months ago, has done in a GSOC project in 10 weeks. The basics of this, now we've improved this, but you see that the high productivity is also exemplified in this example. Talking more about performance, we've worked a lot on basically making this AD framework fast in the past years. For example, really by looking at the system of equations one has to solve in order to get the implicit differentiation going. And there it turns out it's again a nested problem. You have to avert a complicated operator. And this chi0 term here that you have to iteratively apply in order to do the inversion itself also is an iterative problem, right? So you have two nested set of iterative loops. And it turns out that this inner thing can actually be ill-conditioned, in particular for metals. So you see it really needs a lot of iterations. So here, this is the number of iterations over basically the kinds of equations you have to solve. And we've worked on methods, for example, that use the structure, the mathematical structure of these kind of problems to, again, 40% reduce the iterations. So again, something where using Julia, where algorithms are accessible, helps you to accelerate, not necessarily by using HPC type of acceleration, but to understand more about your problem. Another thing I wanted to quickly get into is error control. So if we understand errors along different axes of research, for example, here I'm representing it by different basically resolution and different color. If you basically only are interested in this kind of resolution, you don't need to go to very accurate numerics, for example, to go to very high resolution in the color. Sometimes it's sort of okay to just find some balance in between. But to find the ideal balance, to find the ideal compromise between color and resolution, we need error indicators. We need to understand how much error does actually get induced if I'm sort of cutting down on this or that axis. And this is exactly where, again, mathematics can really make a contribution in order to understand what is the discretization error, what is the error of the model that I'm using here. And here again, we've been at the forefront at trying this in the context of plane wave density functional theory. We've come up in simplified models in so-called band structure plots. That's a very important quantity in this field, where basically you have error bars that indicate you the complete error within the model. So that is basically the chosen basis set size, the chosen numerical tolerances, and so on. All of this is in this mathematically guaranteed error bar. Or for example, more recently, we are looking at more realistic properties, such as the density or really the force in a DFT computation. We're trying to estimate there the errors that come from the chosen basis set size. And the idea, of course, is to push this forward into the machine learning in the future and try to basically use this to balance errors along a larger material science pipeline. We've verified our code, again, using this high throughput framework that I was mentioning. So this was done using automated calculations. And here we're testing some standard structures that probe sort of the physics. And you see our code agrees very well. So blue means good agreement with Quantum Espresso, one of the standard codes of the field. So we are now fairly confident that we're really reproducing the results of other codes rather well, and that the code is ready to be used in practice. All right, how much time do I have left?
We have 4 minutes left.
Okay, that's less than I expected, but at least I want to show you something. Oops.
I'll also allow you some time for questions. You can cut time from your questions.
Yes. Okay, so I have a notebook which shows some things. So one thing I wanted to at least briefly mention here is if, for example, you want to play with the code, in particular, you want to try new algorithms, it's actually fairly simple. So here what I'm doing is I'm actually coding up one of these fixed point algorithms. And what you can do in DFTK is when you're actually running your computation, you can easily just slice in this fixed point algorithm. So for example, this allows me in a Pluto notebook environment to easily tune parameters of the algorithm and directly see what is the effect of actually running, in this case, a realistic system, right? So this is a system of silicon, so a non-trivial system that I'm computing. Similarly, we made GPU support in the sense that you can very easily just do all of this interactively on the GPU. Talking about AD integration, if you have, for example, the computation of a complicated quantity of interest, such as the band gap of silicon, so this is just some code that essentially computes the band gap of silicon doing a DFT simulation. Using forward diff, you can now basically just say, okay, compute me the derivative of the band gap with respect, for example, the lattice parameter, so the one structural parameter of your problem. And again, it will do the SCF, it will call the AD, it will solve the appropriate underlying response problem, and directly give you the answer. As you can believe, we have some nice integration with JuliaMol Sim, but also we can integrate into external packages such as Optim. Feel free to look at this in more detail and ask me for questions if you're interested. All right, so now I'm going to quickly conclude. So as you've seen in the keynote, I have an open postdoc. If you're interested, please contact me. We have a nice workshop coming up in Lausanne in November. There's some people in the audience here already have gladly confirmed to come. Others, if you're interested, please apply. And basically, I think that brings me to the end. I showed you a little bit the motivation and what we're able to do in DFTK at the moment. In the future, we will really want to work on this error control and sensitivity aspect enabled by AD and the numerical algorithms. And we basically want to use this for inverse design, for improving things in surrogates. And we currently also work in the other direction, integrating domain-specific libraries for HPC in the DFT context. There's a library called Sirius that is also developed in Switzerland. We're trying to sort of make DFTK a front end for that, because the current front end they use is in Fortran, and they don't like this. So we are offering to bring it to the Julia world. We are working on increasing composability with JuliaMol Sim, and again, we're working on a tighter integration with this AIDA high throughput workflow, such that our basically algorithms can be directly tested in a real practical context, and we can see if we bring some advantages here. There are some things where you can help. Performance is a big deal, especially if you're a GPU person. I really would like to talk to you. Parallelization, there's some low-hanging fruits where we want to work on. Some AD backends like Enzyme, I think, would also be really beneficial for us, but I simply don't have the time, or we simply don't have the time to work on this. So if you're interested, please let us know. Use the code and let us know if things don't work. I'm sure some things don't work, so please let us know if that happens. With that, I want to thank basically the people from my group, the people at EPFL I'm working with to integrate with AIDA, the various people from the math side I worked with over the years to make these algorithms happen, all over 40 contributors we've had over the past 5 years. And with that, I look forward to your questions.
So, someone has a question. Questions? You.
What happened with lutetium on the error plots? It seemed to be the only one where the simulations didn't agree.
If you have the answer to that, I would be very happy. So the honest. Okay, so I give you the 1 minute answer now, and we can chat about this for half an hour later. So the problem is, while we were doing this, we actually discovered problems in Quantum Espresso. Okay, so or rather in the pseudo-potential file format that Quantum Espresso uses. So because we were not making some approximations that they were implicitly making, and then we had discrepancies. So basically by this comparison, we noted that there was some issue in the way Quantum Espresso and this file format deals with it. So right now we're not sure if this is us or if this is them. So I don't have an answer to that, right? But it's a good question. I don't know.
Thanks for the talk. I wanted to ask about this computation of the second derivatives of the potential energy, particularly the algorithm that you implemented for estimating the preconditioning matrix.
This one.
Yeah, could you talk more about the method?
Yeah. Okay, so the math point of view is that the second derivative of the energy actually turns out to be this guy. Okay? And so what we are doing is, instead of inverting this exactly, we make an approximation for this chi0, which turns out to be the expensive object. And the approximation we use comes from homogenization theory. So we do a so-called row-sum mass lumping. We take this thing, which is basically a matrix, and we integrate everything on the diagonal. And from a physical point of view, what you get is the so-called local density of states. So it's actually really funny that a mathematical procedure turns out to give a physical quantity. So the point is that this local density of states turns out to be relatively cheap to compute and a good approximation for this chi0. So what we're doing is that we're just inverting this operator here once we have done one step of the self-consistent field. And we don't use the exact chi0, but we use this local density of states approximation. And this turns out to be able to really distinguish where is a metal and where is an insulator in your system automatically, and therefore it automatically uses the right kind of preconditioning for these kind of systems without you doing anything. Yeah.
More questions?
So you were showing these band gaps that you compute and the error bars that you are able to, and I was wondering, like, people use these GW methods for band gap calculations, and does this get you closer to?
Yeah. So I glossed over the details there in this paper, but this is actually not even DFT. So this is a so-called linear Hamiltonian, right? So this is a very simple model which is very wrong. So the goal here was to classify all the numerical errors. So floating point precision, the eigensolver tolerances, and the discretization error, and forget about the model error, right? So I can't answer this question because we actually didn't investigate it here. We just assumed that this model was ground truth, which we knew is not true, but we at least dealt with all the other things, right? So capturing model error is really tricky. Niklas works on one aspect of that, but it's really an open problem how to do that properly. Yeah.
Okay, thanks.
Well, actually, I have a question.
Yes.
So I saw that you have an algorithm to determine the damping constant. I was also always like twiddling with it. Now I'm curious how that works.
The way this works is essentially by this realization here. So essentially here we have a simplified version of the SCF, and we also have a damping parameter here. And now when we do one step, so we want to go to xk plus 1 starting at xk, we now ask ourselves the question, how large at this particular step should we choose alpha? However, since we know that overall this is a minimization problem, we can just do a line search along the direction given by the gradient and find the point which is lowest in energy. Okay? So far, so trivial. The problem, though, is that computing the gradient and the second derivative, which is what you would need to do this line search properly, is quite expensive. So we have some tricks to basically shuffle terms around such that the things you compute are the things you anyway need in the next SCF step, such that we can basically do like recycling of the computation that we have done before. So effectively what this means is that in this setup, one SCF step is as expensive as the number of line search steps you need. So typically we need 1 or 2. So it means that the SCF steps are usually exactly as expensive as they would be in a standard algorithm, or at most twice as expensive. Right? So it can happen that one step is more expensive, but at least for very complicated system, such that this Heusler alloy, you don't need to fiddle so much with the damping, because as you see, it actually automatically goes up and down quite a bit. Yeah. But again, in the paper are the details, and I'm happy to give you more of them. But this is like the high-level summary.
Okay, thanks. More question?
Thank you. So, I mean, I know the focus is a bit different than most like quantum chemistry packages that we have, but you've shown like how much shorter your code is in comparison, and then how good the element description or whatever you benchmark there was.
Yep.
Did you also look at speed for some like molecular systems? Like,
well, molecular systems and plane waves are generally bad, right? So the answer is we're going to be as bad as all the other codes. Yeah. So that's the short answer I can give for molecular systems. You can do it, but I mean you have to put a vacuum around it, and that makes you pay, right? There's some tricks in the literature. There's some tricks you can play, especially when you have surfaces where sort of half of it is vacuum, but we haven't implemented those. Yeah.
I really liked how you can play with the code in the Pluto notebooks. Really.
Yes, so do I. It's great for teaching too.
More questions? I actually have one more. So,
sure.
So you talk about preconditioners, and I always have a struggle finding a preconditioner works for my systems. How do you go around finding which one works for you?
So in this case, I use maths, and then I know that basically this approximation is sound, and so that this has the ability to capture the majority of systems. But okay, I didn't show this, but one thing we can actually do in DFTK is we can build the iteration matrix corresponding to this SCF with and without preconditioning. And so then I can actually look at the eigenvalues of this matrix using Krylov-Kit, for example, because all of these objects are available as simple functions or operators, and you can use them interactively composing with other Julia tools. And then I can actually look at the spectral properties of my SCF. And then I can actually see, okay, with this setup and this preconditioner, my spectral properties are better. Right? So I mean, of course, in general, when I do production calculations, I just use whatever setup and run the calculation. But for the debugging here, to make sort of this development, I can actually reduce my system, go to 1D, make it simple, and use Julia tools to really query the mathematical properties of my SCF, and in this case, sort of design the preconditioner such that it sort of fits the system under study. Yeah, that's sort of the big advantage of this package over existing codes, really, to have this simple playtesting and scaling up to a realistic setting where you can do real calculation.
It would be great if you have some sort of guide or tutorial on how to do that. I will be interested in that.
I think we have exactly that aspect as an example on the website.
Okay,
this dielectric matrix diagonalization. Yeah.
Okay, thank you. More questions? No? If not, then I would like to thank our speaker. And then we can have lunch.
Welcome, everybody, to our Julia for HPC mini symposium here this afternoon. We have a couple of talks. So originally we planned for 20 minutes per talk, but one talk was cancelled. So please stay within the 20 minutes, including some time for questions. But we will have 22 minutes officially on the schedule for each talk. So don't be confused by this kind of weird time. I don't want to steal your time, so the first talk will be by Boris Kaus and Ludovic Grass about developing fancy supercomputing geoscience applications using Julia.
Okay, thank you very much. My name is Boris, and I'll share the talk with Ludovic. So we are dealing with geodynamic applications on one hand and ice dynamics on the other hand. You may be wondering what the heck is that about and why are they similar? Well, geodynamics on the scale of the plate, on geological timescales, the Earth behaves like a fluid, a complex fluid with very complex behavior that can break, that can float, flow on a viscous manner depending on what the temperature, stresses, etc. are. On the other hand, we have ice sheet dynamics, and the basic equations that govern this are quite similar. And in both cases, we have a very big difference in scales that goes on the scale from the Earth, from thousands of kilometers, to the scale of shear zones that are hundreds of meters that play a crucial role in determining whether we have plate tectonics or not. And the same happens with ice sheet dynamics, where the flow is a very large ice sheet, but much of this deformation is localized in ice streams that are much smaller in scale. So in other words, we need high performance computing to resolve all of this, and that is the background of the GPU for Geo project we have been having over the last few years, where the idea was to build a unified suite of software tools for both ice sheets and geodynamic applications. And the focus here, as the name says it, is on GPU computing, and Ludovic will later show the results of their allocation, extreme scale allocation on the biggest HPC machine in Europe that is GPU based. So classically, codes in this community have been big monolithic codes with 50,000, 100,000, 100,000 of lines of code. That makes it very intimidating for a new PhD student to start working with these codes or add new features to it. And thanks to the power of Julia, it is possible to make this in a much more modular sense. And we have therefore developed a range of packages that together can have the same functionality, but can also be used individually. And the main advantage that we experience with this is that we have many more contributors to each of the individual packages, because it's easier and less intimidating for newcomers to add to this. So in GPU for Geo, I have a bunch of packages we will discuss later. They are developed on a bunch of tools. Parallel stencil and implicit global grid has already been discussed in the last few JuliaCons, cell arrays, Gemini, and then we are basing this on things like CUDA.jl or MPI.jl. The equations we solve in this are the incompressible Stokes equations, or the nearly incompressible Stokes equations, where the challenge is that the material parameters are very strongly varying and nonlinear. They can vary like 10 orders of magnitude between having melt in one location and having solid rock next to it. They are nonlinear, history dependent. We are using in both applications a staggered grade finite difference formulation, because that is a stable scheme that turns out to be very, very scalable and works well. It's good for high performance. Irregular boundaries require some special care, and that can, for example, be done with an immerse boundary methods. We have the packages we have been developing are based in basically two organizations, Julia Geodynamics and Pseudo-Transient Solvers. And there's lots of people that have contributed to that. Albert Montserrat is one of the main postdocs that has been hired in this project, and he does an incredible work. Same with Ivan, who's here and gave a talk, what was it, yesterday or so. So if you want to have a look, give this a look. So one of the packages, what we are often dealing with when we are trying to model geological systems is that there is lots of data available, but in all kinds of formats. And creating an initial model setup from all that data is actually not that straightforward. And that is why we have developed something called the geophysical model generator that basically allows us to import the data, project them from spherical coordinates to Cartesian coordinates, create an initial model setup, run simulations with that, and get the simulation results back and compare it again with the available data. And that is a very simple package, but it's actually still quite useful to collect different data sets. And this is an example of the Jura Mountains in Switzerland, where we automatically download the topography of the region. You take a geological map, drape it on top of it. You have a sketch from the geological paper that you can put as a cross section, simply as a screenshot from the sketch, and you have like some digital map of where the basement rocks are. So that is something that we use as an input model generator. The core, or one of the main packages we are dealing with, is called GeoParams. And GeoParams deals with the fact that many geodynamic codes have very complex constitutive relationships. Viscoelastoplastic, they are nonlinear, and much of the complexity of developing a geodynamic code is actually in developing this kind of constitutive relationships. The point is that these relationships, they are always pointwise calculations. So it doesn't matter if you have a finite element code, a finite difference code, a spectral element code, you always need to do this kind of calculations, and they're independent of the discretization. So the idea of the package is therefore to create a database of lab-based parameters. Takes quite a bit of time to collect all of that. It provides a computational engine. It provides plotting routines, unit conversions. It's GPU compatible and it's differentiable, and it allows you to set up a complicated constitutive relationship like written here, simply on the command line, and then you get a little graph of how this looks like in principle, and you can extend this at free will. And that is quite powerful because we have then one simple callback API that is compute tau second that updates the stress tensor. And if your code uses this, then a new constitutive relationship added to GeoParams will automatically be taken into account. So you add it once, and then you have a whole range of codes that can use this. And this is actually quite powerful. It works on GPUs, and it is also relatively fast. So let's give you a quick example. This is a typical equation of state where density depends on temperature and pressure with a few parameters. So if you would just code this up in Julia, you would call this compute density 0 with a bunch of parameters. And we have also coded this up in GeoParams, which is basically the same. If we compute this and benchmark it, we see we have 1 nanosecond here, and we have the same time there. So we lose no time by using GeoParams. Typically, we have in our simulations not one type of rock, but we have typical many different types of rocks. And we often code them up with different phases. So phase 1 is rock type 1, and phase 2 has slightly different parameters. So let's have a look at how you deal with that. So if we have the handmade kernel, then you can say, okay, we initialize an array of phases, which is the type of rock that you have, and then the naive implementation of that would use a if statement, and you loop over each of the phases, and depending on what you do, you use these parameters. And you see in this particular example, this takes 192 nanoseconds with branching. Now you can, of course, say, well, using if statements is bad, so let's get rid of that. You get a faster code. So if we do the same without if statements, it is indeed a little bit faster, 160 nanoseconds. But if we do the same with GeoParams, the same type of loop, we are 4 times faster, and that is because we are using multiple dispatch and a few other tricks in the background. So you see that this actually really brings an advantage of having this in a central package rather than having to code this up yourself in each individual code. You can also compare this with a C++ implementation here, and you see that the case, and this is a 2D case, you see if we use the branching, then we have about the same speed between C++ and Julia. Also with the branchless case, and if we use GeoParams, we are still a little bit faster, which is probably that because our C++ implementation is maybe not totally optimized. But in any case, it shows that Julia certainly is compatible with the compiled language, and very useful because it is modular. So just to give you an example of how this works in practice. In practice, in your code, you would specify the different material parameters in your input setup. And then in your actual code, you would run this kind of simulations. And this is now done on a GPU using a so-called pseudo-transient solution method that simulates the breaking of rocks. Another ingredient in many of the geodynamic codes is that we use the particle and cell advection scheme to deal with large deformations and complex geometries. And this has been implemented by Albert in the package Just Pick that works on multi-GPUs and on CPUs. Just Relax is our code that basically combines all of this into a bunch of benchmarked examples that run in 2D and 3D on CPU and GPU, on multi-GPUs. And here are some examples of using Just Relax to simulate the subduction of tectonic plates on a 1,000-kilometer scale in 2D and 3D. This is an example of a PhD student working in mines who is currently trying to simulate massive volcanic eruptions and how they happen on a million-year time scale. And you see the breaking of the rock and a big magma chamber. We can also, so this is on a scale of 20 kilometers. We can also look at this on a much smaller scale. This is the scale of 100 meters, where we simulate what happens if you have magma that is injected into the earth, into rocks that are solid. Turns out the magma cools, it starts to crystallize, the crystals are heavier, it sinks down, it heats up the host rock that starts melting, and these are phenomena that we can simulate in a rather straightforward manner. If we're only interested in looking at the thermal structure of magmatic systems, there is a package called Magma Thermokinematics, which simulates this in 2D or 3D. The advantage is that it is a very short code, so it's very easy to apply it to different locations. And again, this works with all the packages I discussed before. So if we add a new type of melt or heating, crystallization, parameterization, we would do that in GeoParams, and then this would then be available in all the codes you just saw before. Yeah, so that makes it very modular. So at this stage, I would like to hand over to Ludovic, who will explain you how they broke the world record of doing the world's largest resolution simulation of a Stokes problem a few weeks ago.
Thank you. Yeah, well, thank you. Hi, everyone. Well, I don't know. It's at least European scale on a kind of custom code. It's like certainly some good numbers. So yeah, in the remaining of the presentation, I'll talk a bit about some of the HPC insights of the project, focusing more on the ice flow part of what we were doing there. So as Boris introduced, like one of the things that is interesting to us is this kind of localization of flows. So kind of why on this, for example, like Antarctica, Greenland, or big or smaller ice sheets, like nothing moves, but unless some very few region where all the action happens, and kind of these streams, as they called. And like here one sees one where like fast flow in the middle, and these stream margins where you have like extreme shear deformation. And this is just to give an idea of like an idealist setup, but basically one has like these corridors of fast-flowing ice, and the question is like, well, what leads to what handles the stability? And we're investigating these kind of thermomechanical feedbacks, such that, for example, shear heating, like you have in a region where it concentrates stress and strain, it would heat up, weaken the ice, and like start to get this localization process. But to do this at large scale and in 3D, one needs tools, and tools that be able to leverage GPUs. So I kind of won't make the whole GPU propaganda, but basically, kind of GPUs are currently the way to kind of get extreme scale computation at extreme scale performance, and so we are developing these fast ice solvers, and they are like just given overviews. So well, basically for now we handle full stokes in isothermal and thermomechanical setting, but ideally we have a list of adds-on. And yeah, so there's some tooling around, so how you pre-process and post-process, like treat this immersed boundary condition. That's pretty challenging because while it needs to be, well, distributed and like kind of one cannot lose performance on that. And obviously, like for example, having immersed boundary, it by construction seems to be like, well, I need to do a lot of checks, they're potentially branching, etc. So there. Well, we do it with a bit kind of using a variation approach, but kind of using masking rather than branching, so just things that don't kill your performance on the GPU especially. And well, we rely on a kind of core package that provides the functionality to handle grid fields and operators that Ivan mostly spent time to discuss earlier this week. But the main idea is really that we need to target GPUs and latest generations. So for example, latest Grace Hopper from NVIDIA, or like what we were now having allocation on, like AMD, these MI250, which are like one of the latest available AMD GPUs. And this is kind of one project that we currently, kind of in the final phase, which is called Stream, and where we got one of the few extreme scale allocations, so the largest allocation on a European supercomputer, the largest in Europe, which is Lumi. And yeah, it has about 3,000 nodes, and each of these nodes has 8 of these MI250X GPUs. And so we got awarded 5 million GPU hours to make a kind of different type of simulation, including like large runs. And in this project, we were focusing on first on this on the Vavilov ice cap, because we realized that it was like there's some challenges on the way. So this has like some regarding like geometry and aspect ratio and boundary condition. This was like a first thing to start with, and so we're towards like doing different kind of runs there. And so one sees like the color scale is like the magnitude of ice flow, and the red part is the region that we see on satellite images where there's these streams that localizes, and such kind of simulation, they're like really extremely expensive. So that kind of wouldn't be possible if you don't run on many nodes. And so regarding the performance, so a part of doing some simulation, we were also doing benchmarking, testing, fixing a lot of things, but yeah, like recently we finally kind of have an implementation that's more or less stable, and we converged to something like that was kind of trying to get everything the right way, such that so what you see here is like a weak scaling. So we run a kind of a 640 cubes on one GPU. That's the local problem size, and then we increase the problem size together, like linearly together with the number of GPUs, such that using more GPUs, they all run the same local problem size. And so we went from 1 GPU to 21,952 GPUs, and timing the same amount of work, local work, we basically lose only 3% of kind of time from going from one to basically the full machine. And this is like running Julia that was, on the machine that was downloaded with Julia up, and MPI preferences that was, just using MPI preference to set up where to find the MPI library. So it was like a 2-click setup, and it's pretty cool that kind of, running, just installing Julia up on the supercomputer, hitting once the MPI preferences, and having, spent some time on making the implementation behind good, it kind of just works. And so we're pretty excited about that. And so the whole thing here, and quite some work went into this overlapping communication with computation, because at large scale, it's where you would lose time. So while increasing the number of GPUs involved would increase communication between them, between processes, it's all point-to-point, but still overall it kind of increases some entropy in the machine, and then you could easily, well, without this, it would just go down to a bunch of under 10% fairly quickly. And yeah, and again, Ivan gave some nice insight in his talk that is available online. So how we achieve this, especially, so here we implemented everything is task-based, like Julia idiomatic, and so we had some things we needed to overcome some little things. So well, we figured out that these tasks could be fairly expensive when they hit the finalizers if we spend a lot of tasks, and then yeah, we kind of had workarounds and they seem to work. Another thing that we started to look at, but that will be further pushed in the hopefully granted follow-up project, is differentiable modeling. So, well, now we have these distributed GPU codes that can solve Stokes-like problem, and now we're looking into ways to make differentiable modeling, well, they can leverage differentiable modeling, and the solution scheme we're using, these iterative solvers, we kind of, well, found or revamped a way to be able to use them to solve the adjoint problem. And then if you have a way to efficiently solve forward problem, to efficiently solve an adjoint problem, you can start to do inversions at large scale, which is also a topic that's at least what I find super interesting. And there we combine it with enzyme, and basically that's what I'm showing here. So if we have a forward problem on the top, the way one can phrase the adjoint problem in our case would require to compute this transposed Jacobian, and this we can get in a black box way on the GPU in a distributed fashion from enzyme, which is fairly cool. But there's like, I guess maybe later or next year there would be if that works out, like, and we have the project, there could be a talk on that. But now we have a sandbox. We're looking at the glacier in Switzerland, the Aletsch Glacier, for those who recognize. And so, well, here it works. So we were inverting or trying to retrieve the sliding coefficient, so how much ice deforms versus it slides on the bedrock to fit the observations. So the observation is the truth. In the middle is the velocity one would get if one doesn't have any sliding, so only ice deformation with a simplified model. And then the third pane is the velocity when you have this sliding at the base that we retrieve this automated work. Yeah, I'll skip that one. But maybe just to finish also that in general, as Boris said, like, so there is maybe this shift in community. So we tried in geodynamics or Earth computation, Earth science, in geodynamic and ice dynamic as abroad. So slowly, well, more and more people use Julia and Julia at scale. We're teaching a course at ETH that uses, well, Julia, GPUs, and all these same things, and yeah, and have some, well, activities around it, and that's really, there's some nice momentum around. So yeah. To have some time for question and discussion, I leave you with the summary and the conclusion here. And yeah, well, I thank you for your attention.
Yeah, thank you very much. And in the interest of time, the next speaker can already set up everything. And while he's doing that, maybe we have time for one quick question. That's the first one I see.
So I was wondering, the solution methods that you use, are they all explicit or implicit, or is there a mix? And if you need to solve linear systems, are there already good solutions that work massively parallel on GPUs?
To get the extreme scalability, you have to use explicit solution methods. It doesn't work otherwise. The general framework, for example, for using geoparams, also works with implicit codes and with automatic differentiation. So in principle, you can also write the implicit code using the whole framework, but I don't think it will scale to the same to the same size of machines. Yeah. But the advantage is we can reduce duplication of work a lot with this.
Maybe I can just add a little comment. So the iterative scheme, it uses kind of, what we're using here is like, so both cases so we use kind of iterative solvers but so the solution is implicit, but the iteration strategy is an explicit one. But yeah, so that's kind of, it's still implicit solution, so it's not explicit. Yeah, it's kind of, it solves like elliptic equations, so we have a implicit solve.
Great. Thank you very much again. And now it's time for our next speaker. It's Sriharsha Kandala from the Climate Alliance, and he will talk about portable communication interface for Earth system modeling. Please.
Good afternoon, everyone. Thanks for coming. My name is Sriharsha Kandala, and I'm a software engineer with the Climate Modeling Alliance at Caltech. So, a quick intro about us. We're a group of like climate scientists, software engineers, mathematicians working on developing what's called an Earth system model. So this is a joint collaboration between Caltech, MIT, and JPL. So these Earth system models use a lot of parameterizations for various pieces like clouds, turbulence, convection schemes, etc. And based on the quality of these parameterizations, this can result in uncertainties in climate models. So the objective is to use update these parameterizations based on global observations and targeted high-resolution simulations so that we can produce really accurate climate simulations. Our software stack is built in Julia, and we support distributed GPU and CPU simulations. I'd like to thank our sponsors. So this is a quick snapshot of the subset of our ESM software stack that contains the climacoupler. There are multiple levels to that. At the bottom, we have this basic building blocks like ClimaComps, which provides those device specifications and the communications interface. We have the ClimaParams, which provides the physical constants, the universal constants, and other constants. Then we have the thermodynamics package, which provides us the moist thermodynamics relations. At the next level, we have the ClimaCore, which provides the spatial discretizations for our simulations, the needed infrastructure for the spectral elements and the finite difference. Similarly, we have the Clima time steppers, which provide the time stepping code. Then we have the RRTM-GP, which provides the radiative fluxes. Then the cloud microphysics, which provides those cloud parameterizations. And then the surface fluxes, which provides the interface fluxes at the Atmos land and Atmos ocean interfaces. At the next level, we have this climaatmos.gl, which is essentially the die-core, which builds on the packages in the lower levels. Then we currently prescribe ocean temperatures and sea ice concentrations, but the plan is to eventually use Clima Ocean from MIT coupled with that. And then we have a Clima land and a simpler approximation of a bucket model for the land model. And then the coupler couples the die-core, ocean, and the land model. So a quick look at the dynamical core. We essentially solve the conservation equations for the mass, momentum, energy, and transport. The radiative fluxes and the source stems fit into these equations from the various source packages. So a quick look at the discretization. We use a hybrid grid for our spatial discretization. We use the spectral element discretization in the horizontal direction, and then we use the extrude the spectral element grid in the vertical direction, and then we use staggered finite difference approximation in the vertical direction. And our grid is a pancake-like grid, which is stretched in the vertical direction. We use generalized coordinates and we use covariant velocity components. We have like a high aspect ratio mesh, and we use horizontal explicit, vertical implicit time stepping for our production cases. In the horizontal, we use hyperviscosity for stabilizing the horizontal momentum, energy, and tracer transport equations. For the turbulence and convection schemes, we have a simple boundary layer diffusion scheme, also called the Frierson scheme, and then we have our EDMF model. So a quick look at the horizontal discretization. We use what is called a HP mesh. Here H stands for the outer mesh, and P is the degree of polynomial approximation within each element. So we have the sample spectral element mesh with 4 spectral elements in here. So here with the continuous Galerkin spectral element method, all the degrees of freedom on the interface of any 2 elements are redundantly represented. And then once we discretize the spatial equations using Galerkin projection, the details are not that important for the talk, but we will eventually end up with a term that looks like this: mass times the derivative is DSS of RHS, where the right-hand side is completely can be evaluated completely local to a spectral element, and thereby completely local to a given process. So the major communication cause for this algorithm comes from the direct stiffness summation. So we have this pure direct DSS, the normal DSS, where we just add up. So in the picture, you can see the local degree of freedom numbering for each of the local spectral elements, and the corresponding global numbering in green, which needs to be the same at the end of each simulation, because this is like a C0 continuous approximation. So what we need for our case is this M inverse, approximately the M inverse times direct stiffness summation of the RHS. So, and there is a nice property that when we use the quadrature grid to coincide with the physical grid, we can have a reduced upcount when evaluating this combined operation. And it essentially reduces to a Jacobian weighted average at each of the redundant degrees of freedom to compute the G. So all of our communication infrastructure is stored in our topology data structure. For example, on the right, there is a picture with about 16 spectral elements and partitioned with a space filling curve across 4 processes. So the topology data structure contains all the information needed for the communication infrastructure. For example, it contains the partition information. It stores the process neighbors for each of the processes. Then it, for local elements, it classifies them into fully internal elements and elements called perimeter elements, which exist at the boundary with elements from other processes. It also provides information on the interior and ghost faces and interior and ghost vertices, and it also stores the data for the representative ghost vertices, the number of unique faces and vertices that needs to be communicated to each process neighbor, etc. And this also contains the information needed for constructing the indexing arrays for loading and receiving the send and receive buffers for the DSS. So the next item is the graph communication context, which we have in ClimaComps. So for example, here is a data structure which contains the persistent send-receive graph communication context. So we first build the connectivity graph from the topology information. For example, in our case, it's a continuous Galerkin. So vertex connectivity is what determines if spectral elements are connected to each other. For example, in this data structure, we have the send. So we store the send and receive ranks for each of the processes and the corresponding send and receive buffers. We tend to use the DSS inside a time loop. So to minimize the overhead, we use persistent MPI communications as a default. We also support non-persistent communications, and this works with both the GPU and with the CPU and GPU buffers. And in case the MPI is not CUDA aware, it does some internal buffering, which is a bit more expensive. So here's a quick snapshot of our graph communication infrastructure for the DSS. So we have a start where we post the sends and receives, and then we have the finish where we use a wait out statement to make sure the receives happen correctly, and then we do an optional probe in the middle using the progress. So the first stage in this DSS is actually building the DSS buffer. So it's built based on the information provided from the topology data structure. So it builds the transformation signature for the perimeter array. So since in our case we use local coordinate systems for each of the spectral elements, and we store velocity on a covariant, we store the covariant velocity. So for the vectors, we need to first transform it to physical velocities before we actually apply the DSS. So that's some extra work involved with the vectors. So the DSS buffer classifies the fields into scalar, covariant, and contravariant bins for the transformation purposes. For the vertical component, given the construction, we do not need to do the transformation for the 3D velocities. And then we build, the DSS buffer also builds the perimeter data array on which the DSS results are actually stored. It builds the indexing buffers for loading and unloading the communication buffers, allocates the send-receive buffers, and initialize the graph communication context. So our weighted DSS algorithm is split into 3 pieces to enable communication computation overlap within a given DSS. The first part is the weighted DSS, where we fill the buffers and start the communication. Then we do the internal DSS while the communication is happening, and then do the ghost DSS after the communication is finished, which gives us this overlap, the communication computation overlap. So the first piece is the weighted DSS start. This piece weighs and transforms vector fields to physical fields as needed. So this calls the DSS transform on the perimeter elements first, and the results are stored in the perimeter, on just the perimeter elements, and the results are stored in perimeter data. Then we compute what is called the local part of the weighted DSS on the ghost vertices using only the information from the process local vertices. So this helps us reduce the size of the communication buffer a bit. And the results are stored in each of the local vertex locations in the perimeter data. And then we fill the send buffer and initialize the communication. The second piece is the weighted DSS internal. So we transform now, while the communication after the communication has been initiated, we apply the DSS transform on the internal elements, and then store the results on the perimeter data, and then we do the DSS on the local vertices and faces. And in the third phase, we finish the communications. We add data from the receive buffer to the corresponding location in the perimeter data. So for the ghost vertices, the data is only added to the representative vertex, and then the data is sent from the representative vertex to all the redundant vertices. So, and then we untransform the data as needed for the DSS and store the result back in the original field. And for running this on the cluster, there are some additional considerations. For example, unlike CPUs and the GPUs, we need to make sure the local MPI, each local MPI rank picks up a different GPU. Sometimes all ranks tend to pick up GPU 0, and that gives, for obvious reasons, really bad results. So we need to make sure it picks up, each local MPI process picks up a different GPU on the node. And then we also need to bind MPI ranks to NUMA domains. When you assign multiple threads to a GPU, we need to bind the CPU threads in the NUMA domain to this GPU, otherwise it can be inefficient. So this is a quick representative workflow for a normal DSS. So we first set the device. We can set the device to CPU or GPU, and we also support single-threaded and multi-threaded CPUs for the device. Then we set the communications context. Here it's the MPI communication context for distributed simulations. Otherwise, it can be a singleton communications context. Then we go through the usual process of building the domain, the mesh topology, space, and then the fields. Then we build the DSS buffer, and then in the time loop, we can just evaluate a DSS at each time step. At each of the time, first we do all the local operations and then apply DSS, and this happens every time step, and sometimes every stage of the time step. So coming to we did some preliminary scaling studies. So we have an aquaplanet simulation with cloudy sky radiation, a Frierson diffusion model. We did both 0 and 1 moment cloud microphysics, and we used the strong stability preserving time stepper. We use horizontal resolutions from 55 kilometers to 13 kilometers. We use 64 vertical levels. The simulations are done on Deraco supercomputer at NCAR. It has a total of 8 nodes with about 4 A100 GPUs per node. We used simulations with processes in the range of 1 to 256 GPUs for this study. So we see good, these are the strong scaling results for this simulation with the zero moment microphysics. We see that the scaling efficiency is in the higher 90s, up to about 300 horizontal elements per process. 3,000 horizontal elements per process, after which the scaling efficiency could drop down. That seems to be a good size at which the GPUs are relatively saturated. So on the left, we have SYPD versus the number of GPUs. SYPD is the simulated years per day versus the number of GPUs. And on the right, we have the scaling efficiency versus the number of GPUs. So a quick summary. We built this portable interface which provides the communications interface for all the components in our at system model stack. We see good, strong scaling results on the GPU from our preliminary runs. In terms of outlook, we would want to try to increase the overlap between when computing multiple DSS on multiple fields to see if that further increases the scaling efficiency. And we also want to explore the model where currently the current model places each GPU on a separate MPI process. We want to explore the model where we can place multiple GPUs, or to be specific, a full GPU node and a single MPU process, and run multiple processes. Yeah, thank you.
Great, thank you very much. And again, in the interest of time, I think the next speaker can already set up everything, and we have time for a question.
Well, thanks for your talk. I just have a question, like why are we reporting strong scaling on multiple GPUs while kind of what we experience is like usually on the GPU there is a specific optimal problem size that works well, and then from then it makes more sense to go with the weak scaling?
We wanted to look at both the strong and weak scaling numbers. We just started the scaling study, and this is like the first. For the weak scaling, we see close to 100%. but we didn't do the weak scaling study yet on the cluster. We just did it on a local cluster with 4 GPUs or so, but we need to extend it to the, to Dereco.
Yes, thank you very much again.
But we have to be very close then.
Yeah, you should just stand there and it should work. If you want to move around, then you can take this one. I'll introduce him and I'll give it to you.
This one. Yeah.
So our next speaker is Samuel Omlund from the Swiss Supercomputing Center. And if everything is set up, he will tell you about from a single CPU, single core Python implementation to going to multi-GPU Julia implementations.
And does it do one slide or it starts to move then? Can you try?
I'll sit there.
That's not moving, so just like.
Yeah, can you?
You better press with a few rings.
Okay. Yeah. All right.
Okay. Thank you very much.
Yeah, thanks a lot for the introduction. Yeah, I'm Sam from CSCS, and in this project there were some collaborators from Maastricht University, and this is Vaishnavi Narayanan and Mario Senden. And I really personally enjoyed this project very much. I thought I need to do a talk about that. It is maybe not the common talk that you would give to talk really about the collaboration and how we could actually go from single core Python to Julia multi-GPU. So yeah, what happened is that we have this human brain project, this huge project, the biggest project in Europe ever funded, and so CSCS was part of it, and so they came to CSCS and said, yeah, we have here a Python application, and now we want to run it at scale, and because we cannot solve our problems, right? We need supercomputing, and so yeah, they kind of wanted to have advice to do in Python some parallelization, and so I thought that's an opportunity to make something great out of it, and so I said, yeah, let's see what we really need when we want to go from a prototype to supercomputing on a GPU supercomputer. And so yeah, so I said, okay, what's the first step? Well, we need first to have a suitable algorithm, right? We cannot just use whatever single core algorithm we used. And we'll talk about later what we did here. Then the second step. So typically people would go to C or C++, right? And I would say, luckily in this case, they did not yet have a C or C++ or Fortran code, so I could say, well, let's do it in Julia, right? And so this way we avoid this two-language problem right from the beginning on. And but then we have the next issue that a prototype, even in Julia, is not really what is a supercomputing application, and so we need because we need to have a multi-threaded or, well, for GPU supercomputing, CUDA or ROCm, AMD GPU kernels, And so we need to use also certain packages that allow you to really unify prototyping and production. And so parallel stencil is something that we used here to do that, to make architecture agnostic code where prototyping and production is unified. In other projects we use also implicit global grid in addition. Here we use then just MPI, MPI.jl. Yeah, by the way, in the talk that I will give later, I will talk about parallel stencil, implicit global grid, and so on, all our building blocks, if you want to check it out. Then you say, okay, now we kind of solved these problems, but wait, there's actually one more thing, because now these domain scientists, they are completely used to Python in this occurrence, and said, okay, I don't know anything about Julia. Now suddenly I cannot throw everything away and comfortably work with that, right? And then maybe I don't trust the results because I don't trust my skills in Julia. And so I said, okay, we need to have also something to slowly go to Julia, to have a certain transition phase. And I will show here in this talk later what we did to have this transition. So the important thing is to keep Python in the game for a while. And then, of course, always when we do supercomputing, well, we want to evaluate the performance in an absolute manner at some point. Not just say, okay, we speed it up by, I don't know, 10 times or whatever. Is that now good? Or 100 times? Is that good? Right? But to really try to understand how close we are to the actual peak of our hardware. Yeah, and so for that we use an effective memory throughput metric, which I will very briefly outline later as well. So this is the table of content. After the introduction, I will quickly describe the application, the domain science application, right? And then the design of the parallel algorithm that we did. Then explain this approach for the seamless transition from Python to Julia, and then finish with results and conclusion. So, what is this application about? So it is when you come into a room like this, right? You have never been here. You start to look around, to scan, to try to understand what's in here, right? You automatically do that, and while you do that, you move your eyes super quick, like 3 to 5 times per second, and in between you fix, right? You have a saccade, it's called, this movement, a fixation, a saccade, fixation, right? And this is something very interesting for this neuroscientist. And now in this project, they were not interested in figuring out, like many do, what captures our eyes' attention, but to figure out in which order we look at the things. Yeah, and then why is this interesting? It's because if you see deviations from what people usually do, right? How they look around, then you can see that when things don't go right, that this could indicate some problems with health, etc. And yeah, so this has a really, in terms of medicine and health, this has some great potential to try to understand this. Now, how does the model look like? So you see this box there, model, right? and on top is the input, and below is the output. And as I said, the input, as I mentioned, kind of, we're not interested in what attracts our eyes' attention, but the order in which we look at the things. So this is already an input, what is interesting to us. And so these are these maps, these are little images. And then the output of the model, you see below, are then, that's why you see these flashes. So we go then from one interesting point to the next, to the next. This is the output of the model. Then just in general, so we have here in neuroscience, we have not only neurons, but we have populations of neurons, and so we're interested in populations of neurons here. Just as you understand afterwards, when I present the results, what I'm talking about. And so this is a biophysical neuronal network, which represents the 2D visual field. And we have network sizes that range from 1,024 populations up to 25,600. And then afterwards, out of this, we get then connectivity matrices that, in the largest case, contain over 600 million connections. Then, in terms of how to compute that, it involves a lot of large matrix vector calculations, FFT computations, and also some stencil or stencil-like computations. And what makes this like a challenging thing is that the firing rate of these neurons is a nonlinear function. Then to finally solve this, we do a Bayesian optimization and optimize here for 9 parameters. Use 96 images, right? As I said, the input is images that say what is interesting. And so in the original case, it took 280 seconds per iteration for the smallest network. All right, so from here, now we go further to the design of the parallel algorithm. Sorry, until what time do I have?
You have 10 minutes left, including questions.
Okay. So I will speed up a bit. So we had here, the algorithm was, or the idea was to run the application with x times the number of images processes. And this number of processes, we keep it fixed during the whole application, the whole runtime. And each image, each process always works with the same image. And then how does the algorithm work? Well, on process 0, we do all the Bayesian optimization stuff to figure out what has to be computed next, and all the other processes just do the heavy work. So without going into details here, you see the third step. We evaluate on each process a sample, meaning a parameter combination, with the objective function for the image that the process works on. Now this approach, how did we do that to keep Python in the loop while we create a Julia code that would fit on supercomputers? So what we used was then PyCall, and we made the Python application runnable from within Julia using PyCall. So this means we, on one side, we put the main of the application and maybe other large functions in a Julia file using this Py block construct. So this allows you to call Python code directly from Julia with that, yeah. And then in the remainder of the application, the remainder of the application of the Python application, we just could put into some PyInclude, just to include the Python files directly, yeah. And so this means the whole Python code that way is runnable from Julia. All right, that was the first step. Then the second step was to translate then the Python code in very small blocks from Python to Julia. And each time we would keep the Python code in this Python Py block right above the Julia block. And so we would end up with a code that is alternatively always Julia Python, Julia Python, Julia Python, but they don't interfere. They live like in a parallel universe. So even if all your variables still have the same names in the Julia code as in the Python code, they don't interfere with each other. And so this allows you afterwards to do correctness tests, like shown here. Test A equal pi A, and so all the time, everywhere throughout your code, you can have a little verification test, and so that allowed me, without being a neuroscientist, to get basically a first version of the code, to translate it from Python to Julia. That was working, and we knew already it was working, right? Because we had bit identical results all the time. Then collaborators might want to do afterwards further prototyping on Python code, right? Even after that, and that's fine, because thanks to this verification test, we can. As this firstly happens quickly, and also it allows to be always sure things are fine. Things are fine, and so. It's then quite fast to go afterwards to let's say when you update the Python code to update also the Julia code. And then when the collaborators are familiar enough with Julia, you can then throw away the Python code at some point. And it was great to see that really in our project that happened. At some point they said, now I deleted everything, all the Python code, I just stick with Julia. I said, we did it, right? This is a great achievement by itself. Not only that we could run it on a supercomputer, but also that way they really felt comfortable afterwards to work in Julia and throw away the Python code. The effective memory throughput, just to understand afterwards the result. So this is basically to say we compute a lower bound of required non-redundant global memory access and divide it by the runtime. And then the theoretical upper bound of this effective memory throughput is simply the peak memory throughput. So I show here some performance results. First on CPU, because it's easily understandable, and it's good that we can also run it like that. And you see here first in light green, when we run it as one process, what we get with multi-threading. And then afterwards with P processes, we get a better performance because we simply use more data. Because the number of the amount of data increases with the number of processes here. The increase of performance is not dramatic, right? But it's good. And you see we're very close to the peak performance. The green line above T peak is the peak performance. And then in the GPU case, it was really nice to see that already for this the problem size of 4096, as you see the second entry below there. Already in this case, we got to basically the maximal performance that we achieved in general. Yeah, so this was really for me nice to see that we could use this MPS feature that we have to run multiple processes on as a single GPU and really get something out of it. Now here, why does it work so well? Well, because there are quite a large amount of computations without having to do any communication, any synchronization, like between these processes, right? There is no synchronization between the processes for a long time. Then just some quick scaling results. We've scaled it up then to 2,000 GPUs on pit state, and you see we got a 96% parallel efficiency, which is absolutely no surprise because it's very well, by construction, very well suitable algorithm for a supercomputer. Yeah. And okay, yeah. So here the model results. You could see that we got the output there, and that's it. So I leave here the conclusion. I mean, it's not about the modeling, right? This talk. So thank you very much.
Yes, thank you very much. And it's time for the next speaker to set up. And while he's doing that, one quick question maybe. Yeah.
Yeah, thanks for the nice talk. What Julia package did you use for the Bayesian optimization?
That's a good question. The parallel part, we did it completely with MPI. And the serial part, honestly, I don't remember. I need to check what it was. It's now quite a while that we didn't work anymore in this.
Yeah, thanks. Yeah, thank you very much. And it's time now for our next speaker. Tim Bizarre from Julia Hub. I guess many of you already know him, and he will present some advances of the Julia GPU stack, particularly about CUDA.jl and OneAPI.jl. Thank you.
Thank you. Thanks for the introduction, and welcome to my talk. As mentioned, I'll give a brief overview of what we have been doing in CUDA.jl and OneAPI.jl since the previous version of this talk at JuliaCon 2023. I'll start out with CUDA.jl. And as you can see, we've had plenty of contributors this year. So thank you everybody who has contributed to the package. There's been plenty of versions, and I'll give a brief overview of the highlights, especially to an HPC audience or a performance focused audience. And personally, I think that the profiler that we added, the integrated profiler, is one of the most interesting additions to the package, because it allows you to gain quick insights on the performance of your application. It be an entire GPU application or just a single GPU kernel. You can just put CUDA.add_profile in front, and you'll get a summary of the GPU activity on the device, as well as the activity on the CPU that's GPU related. So here, for example, I'm allocating some data on the CPU, uploading it to the GPU, and then doing a simple broadcast addition by one. And you can clearly see on the bottom end where we have the device side activity that there's both a copy and a kernel being executed. It's a summary, so it's ordered by cost. So at the top you have also bolded and in red the most expensive operation that happened. And on the CPU side, we see which API calls were required for that, as well as the statistical distribution of the execution times when there was more than one call to that function. This is some great overview, a great summary of the performance. And if you're optimizing an application, what you will want to try and do is to optimize the ratio of the device being active in relation to the entire trace. So with this very simple operation, we see that the GPU was only active 2% of the time, and the CPU actually was busy 50% of the time doing work to submit these operations. But that's kind of expected with such a simple operation. Generally, with a more complicated operation, you ideally have the device active all the time and the CPU not spending too much time to queue up that work. So this is a summary view. We also have a trace view where you get a chronological trace of the operations that happened, again, both on the host side and on the device side. Because all of the operations are now separated apart, they're not summarized anymore, we can provide additional details on each operation. So again, on the device side activity, we can, for example, show what the launch configuration of the kernel was, how many registers were used. In the case of the copy, we can show how much memory was copied, how quickly that copy went, the throughput of it, and so on and so forth. Again, this can be very useful for optimization, but this can also be useful to just get some insights in how an operation or how an application works behind the scenes. And I'll use it to give some insights on one of the other noteworthy improvements to CUDA.gl over the last year. Namely that calling the synchronize function, which is sometimes something that you often do or happens often behind the scenes, making the CPU wait for the GPU to finish computing. That happens implicitly when you copy memory from the GPU to the CPU, because we need to first wait for those values to materialize. But it also happens when, for example, you call the MapReduce function and you reduce an array to a scalar. Now you have to first wait for the GPU to finish computing and for the scalar value to be, well, available. So in order to do that, we call the synchronize function. We used to call the synchronize function on the main thread of computation. The result of that was that essentially your thread of computation was blocked until the GPU finishes. With the new version of CUDA.gl, we're now doing these synchronization operations on a separate thread. So you can see in the column that the call to QStream synchronize was actually performed on a new worker thread. And this allows the main thread of execution to remain available to perform other work concurrently with that synchronization happening. And this is, of course, great for concurrency. It allows you to overlap synchronization of GPU code with other Julia code. Other Julia code that could, for example, be submitting other work to the GPU or just doing CPU computation. That's all possible. It does also improve latency in some cases, because the old implementation was actually dependent on, it could get blocked with operations happening in libuv, which was always pinned to a single thread. Bit of a detail, but I know that some HPC people have run into that, where the latency of some operations spiked because of contention on the main worker thread. That said, launching code on the thread, of course, involves some overhead as well. So initially, we will be spinning a couple of times to see if the API call is brief enough that we don't need to perform the synchronization on a separate thread. For example, here I'm doing a very short API call, and as a result, we can just do the synchronization on the main thread of execution and instead of sending that work over to a separate thread, which again also involves some overhead. Hopefully that design should make it possible for everybody to use this without inducing additional latency in the application. Nonetheless, I've heard from some people that applications which are extremely latency sensitive even cannot risk running into this. And for them, it's always possible to pass the blocking equals true argument to the synchronization functions in CUDA.gl, which will make it immediately call into the blocking function just like before. And it's also possible to set this with a preference. So if in your local preferences.toml you specify non-blocking synchronization equals false, then we'll also always be using the old implementation that guarantees better latency. Again, in general, I don't recommend this. It's also possible to improve the heuristic on our side when we spin, when we use the thread. So if you have issues, get in touch with us. Maybe we can improve the situation for everybody else. We also did a whole bunch of work on unified memory. So unified memory is a form of GPU memory that's accessible from both the CPU and the GPU. It's not the type of memory that we use by default. By default, we normally use device memory, and device memory is only accessible from the device. And you may have run into the limitation of device memory when porting a CPU application to the GPU and then accidentally triggering some fallback functionality from the CPU side, which, for example, still contained a for loop. The for loop would then be iterating over individual values of the device memory. And when the system detected that you were fetching an individual scalar from a Q-array, we actually throw an error. And that is because, again, device memory is only accessible from the GPU. And if you access it from the CPU, you pay a huge performance penalty. Now, unified memory can help with that because, as I mentioned, unified memory can be accessed from both the CPU and the GPU, meaning that these kinds of scalar accesses are allowed. And this makes it possible to incrementally port functionality or applications from the CPU to the GPU without risking or being afraid that if you trigger fallback functionality, it'll be slow. And this is made possible by optimizations in CUDA.gl 5.4, where here I show the performance of doing the access of device memory. You can temporarily allow it by doing CUDA.addAllowScalar. And as you can see, accessing a single scalar from device memory takes 10 microseconds. Doing the same with unified memory only takes 4 nanoseconds. So that's orders of magnitude faster. And just as a comparison, fetching a single value from a Julia CPU array takes about 2 nanoseconds. So it's in the same ballpark. And of course, benchmarks at these scales aren't really to be trusted, but nonetheless, it shows that the performance improvement of accessing unified memory in a scalar fashion is much, much, much improved. And the main goal of this is to make it much more easier to port existing CPU code to the GPU and without having any performance issues introduced by doing that porting. And to make that a little more user-friendly, we also expose this functionality through the unsafe wrap function. So if you have a Q-array, again, a unified Q-array, which is it has to be unified memory for now, you can convert that Q-array to a plain Julia array using the unsafe wrap function. And then you get this object B as just a simple array object, which you can pass to every functionality in Julia that expects a simple array object. Generally, this isn't necessary, again, because we implement indexing on Q-arrays in a way that works from the CPU, but it's possible that you have a library which has very specific type signatures that only allow array objects, and in that case, you can use the unsafe wrap functionality to derive a CPU array object from a GPU array. This is very intentionally marked as unsafe because you are currently responsible for tying together the lifetimes of those two objects. So if, for example, you have this B object, which is a derived array, if you're using it, but at the same time you let the garbage collector collect the A object, which has the underlying memory, then you'll have issues. So for now, this is an unsafe operation. I envision that we'll fix this in the future, but this is the first step. As I mentioned, this relies on the GPU memory to be unified memory. This may be annoying to specify everywhere. So again, there is a preference now with default memory. If you set that to unified, all of your allocations will be allocated in unified memory. This, I would recommend only to do this when porting functionality. Unified memory also has a certain cost, so it's better to still switch to device memory after you've successfully ported your application and it runs entirely on the GPU. We also have the inverse operation, where if you have a CPU array object, A, you can simply convert it to a GPU object by, again, doing unsafe wrap, but now doing unsafe wrap by a QArray. This is convenient if you have a CPU application and you just want to offload a small part of it to the GPU without having to manage uploading and downloading the results. So you can just simply convert CPU memory to GPU memory. This will use heterogeneous memory management if your system supports it, which would also make this fast. HMM is only available on recent GPUs, and it depends on using the open source NVIDIA driver. So if you have both of those, then this right-hand side conversion is quick and is again an easy way to port parts of a CPU application to the GPU. Another noteworthy improvement is that we now track memory across streams and devices. So if you have a QArray, we actually keep track on which stream and device you allocated it and last used the memory. And this is important when you use multiple Julia tasks. Each task is associated with its own stream. You used to have to synchronize at the end of a task that produced values before using it in a different task, because otherwise you could have a race condition between the two stream objects. Because of us now keeping track on which stream you allocated and used a QArray, for example here I create a task on which I allocate a QArray, I get the object out of that task and I use it in a different task, the main task of the REPL. So those two tasks are using different streams. And as you can see with the profiler here, just simply using that array in some fill operation here, CUDA.jl detects that it's being used on a different stream, and it will automatically insert a stream synchronization operation so that you can safely pass QArrays around between Julia tasks without having to think about, do I need to synchronize this object? Is it safe to use? CUDA.jl will now manage this in the background. And the same applies to multiple devices. If you allocate a QArray on one device, you switch to another device, you start using that object, CUDA.jl will automatically detect we're now executing on a different device, so I need to reconfigure the memory allocation to expose its visibility to other devices. And behind the scenes, this will automatically use peer-to-peer communication, so NVLink or PCIe communication, if that's available on your system. In this example, device 2 is a GTX 1080, which is not compatible for peer-to-peer communication with the V100s I was using before. And CUDA.jl will let you know that it's impossible to reconfigure the system to allow this access. And in that case, you will still have to use an explicit memory copy from one device to another device, which in this case will then stage through the CPU. Finally, we also did some work on improving the GC integration, which will be valuable to many people. Specifically, we're now also freeing memory when you call into the CUDA allocator or when you're synchronizing, because those are two hotspots where at which point it's likely interesting to free up memory. And this was a great suggestion by Gabriel, and the result of which you can see on the right-hand side, where we used to go close to the line of going out of memory, and then we freed up a whole bunch of GPU memory, and over and over and over again. We now will free up fewer amounts of memory, but we'll do it much more quickly. And this is better on the Julia GC, because the GC times will be shorter, and it's also better on the CUDA allocator, because it will have to do much less work on defragmenting and compacting its memory heap. This is driven by a heuristic. So we, at every allocation and synchronization point, we have a look at the memory pressure, we have a look at how memory we freed the last time, how much time we're spending during GC operations, and then depending on that, we decide to do an additional GC call or not. So as a result of it being a heuristic, it may not be perfectly tuned for your application. And because of that, we have this environment variable that we will support for a brief period of time, allowing you to quickly enable and disable this functionality. So I would really recommend people with allocation-heavy codes to try this functionality out, disable it, enable it, observe, hopefully, improvements, if it happens, regressions, and let us know so that we can tune the heuristic to make it work better for everybody. And this is it for the highlights. There's been a whole bunch of other works. Maybe noteworthy is the fact that we shifted our support window, now supporting CUDA 11.4 to 12.5. We also support cooperative groups, which is a new way of programming GPU kernels. And of course, as has been mentioned multiple times already, enzyme support has greatly improved. There's more details about all that and all of I said in the blog posts linked below, which are the ones that we published over the course of the last year. And if you're interested in more of these, follow the blog. And every once in a while, when there's been a significant release, we post something about it on that website. There's also been a couple of OneAPI.jl releases, fewer of them, but nonetheless, we've had quite some contributors over the last year. And I guess for this crowd, the most noteworthy feature is that we now fully support Ponte Vecchio hardware, which means that OneAPI.jl works on Aurora. There's a couple of small outstanding issues with the OneMKL integration, but it only manifests in lesser used MKL calls. So generally, OneAPI.jl should work perfectly fine on Aurora. And we'd appreciate some feedback here because I don't have access to Aurora myself. I got access to some Ponte Vecchio hardware by Intel, but we don't have the CI resources or the CI capabilities to keep track of that. So if you're using OneAPI, let us know about that. We also added support for Windows because we know that some developers are using Windows laptops and then deploy stuff. The main way of using OneAPI.jl on Windows is through WSL. That's fully supported. It's untested in that we don't have CI resources again, but it's fully supported. Native execution we're working on. It's actually possible to compile, load, and execute kernels, but the library wrappers for OneMKL are not supported in native Windows mode. And those library wrappers are important and have been greatly extended. So last year we already supported dense BLAS. This year Alexis Montoison has been helping a lot on additional wrappers on sparse BLAS as well as LAPACK, providing all of these low-level calls as well as integrations with the high-level interfaces in Julia and Julia's libraries whenever possible. This progress has been fairly slow because OneMKL is a C++ interface, so we have to write our own C wrappers surrounding them. So hopefully by next year we might have a C++ interoperability package allowing to accelerate these efforts. And again, there's been many more features. Brief highlights. We support very large array nows, which of course matter to people deploying on supercomputers. The launch heuristic has improved and should improve performance across the board. And we've been continuously upgrading toolchain support, currently using OneAPI BaseKit 2024.1.0. And again, there's been a blog post and there'll be more next year. So subscribe if you're interested. And that's about it. 20 minutes, nice in time. Thank you.
Thank you very much for the nice talk and also for keeping the time. So we do have some time for questions. Yeah.
For the dense BLAS support on GPUs, does it include the tensor versions of the gem call and those variations?
Should I take the mic to respond? I don't know what. Yeah. The tensor operations should be used automatically by the BLAS API calls that OneMKL exposes. To my knowledge, there aren't specific entry points into OneMKL to use the tensor accelerators functionality, is there?
Well, the NVIDIA BLAS library has a separate function call for that.
It's still cuBLAS Gem and GemX, no? And it automatically uses TensorZone.
Yeah, GemX,
Yeah. Yeah, GemX is actually just an extended version of Gem, not necessarily enabling Tensor Core support or not. It's just generalizing the API. Essentially, even the normal Gem functionality should automatically make use of Tensor Cores depending on the precision mode that you have configured. Similarly, with one API, I expect the current Gem call to make use of whatever functionality it's enabled, it be Tensor Cores or regular warp-based multiplications.
Other questions?
Thank you for the awesome talk. One quick point, I may have Aurora access, so we should talk afterwards. I may be able to make that happen. And also thank you so much for helping me out with Dagger on API. Do you think for unified memory, in terms of writing algorithms that are generic, do you think that it is better for algorithms to generally assume that unified memory is available for Q-array inputs, or should they assume it's not, or should we be querying that? Like, what's the right way to write algorithms for that?
They should assume it's not. However, we added it specifically to the type signature. It's a type parameter, so you can actually dispatch based on whether the array you're working with is unified or not. And CUDA.gl specifically already uses that to optimize its copy routines. If we know that we're using unified memory, we just use a plain CPU memcopy, whereas otherwise we call into the CUDA driver API.
Thank you.
Other questions? I see two over there, so maybe I can hand over the mic to you.
How will this whole unified versus separate device and GPU memory evolve from a user point also in Julia if we go to architectures like Grace Hopper where this just will be much tighter? But will we still manage separately where we can, or will we just rely more on this NVIDIA AutoMagic?
I expect to be evolving in the direction of much more unified code. Especially so because, for example, Grace Hopper is a good example because that has gained hardware features to have much more fine-grained faulting. Currently, faulting of unified memory is implemented at the page level, so it's fairly coarse. And with some algorithms that imposes quite some overheads. But with hardware advances, both on the NVIDIA side, but also on the Apple side, where everything is unified, I expect to be moving more and more in the direction of unified memory. Definitely so. We haven't explored that on the Julia side at all. So currently it's the assumption, even on, for example, the Metal backend, that we're using the memory as if it were fully separate. So there's some work left for us to be done there to explore how we best expose that and how we best preserve performance. Example of which can include if you, for example, call functionality, we can prefetch memory, where do we automatically prefetch, do we not do that, and so on. So there's some work cut out for us.
Here. Yeah, thanks for the features and the great overview. We're currently using that through kernel abstractions. So can we all then directly use these features concerning, for example, unified memory, as long as we put the right keywords there when we allocate?
Yes, that will be possible. However, kernel abstractions currently execute only from the GPU side. So there's not that much, unless you're thinking of combining kernel abstraction kernels with, for example, CPU functionality. It would just work by switching over the allocation side to unified memory or switching the preference. So there's no compatibility work to be done on the kernel abstraction side.
Other questions? There? So you can open the mic, please.
Thank you for the fantastic talk. What's the status on kernel side launching?
On what?
kernel launching kernels. So instead of
Oh,
host
dynamic
launching
dynamic parallelism. Dynamic parallelism on the NVIDIA side is supported. I don't think AMD GPU.jl, I'm not sure about, but the other backends, even though the hardware may support it, we don't implement it. But again, on the CUDA.jl side, it is supported, with the exception of H100 and GH200. The reason just being work I haven't done yet. The implementation switched. NVIDIA is using a new mechanism for dynamic parallelism, and we just haven't implemented it yet. But it is our intention to support it across the board. Currently, it does on most GPUs except the highest end ones.
Okay. Is there maybe one question we left? Doesn't look like that. So thanks again. And we're having a small break until 15:40. Thank you. welcome Julian Samaru from Julia Lab at MIT for his talk about unified task parallelism.
Hello, everyone. Can you hear me? Is this working? No? Hello, hello. There we go. We will use this. All right, it's like a fireside chat. Very nice. Okay, so I changed the title of my slide, as some may notice. I realized that I think we need to have a little talk about unified task parallelism before we talk about applications of distributed task parallelism. So I'm the maintainer of Dagger.jl, as many of you probably know, and I have kind of a bold vision that I'd like to talk to you about. So what is this vision? So what if every function in Julia you called was parallel and scalable? This is bold, I know. Just go with me. What if every function you called was ready to run on GPUs, any kind of GPU? What if every function you called adapted itself to your hardware? Say it's parallel scalable beyond just a single device, and it knows the GPUs you have, it knows the CPUs you have, it optimizes itself. What if you didn't have to rewrite your code again and again and again for, different hardware setups? Users have different setups. And we want our code to work great everywhere. And what if this library already exists in Julia? So my assertion is that's Dagger. It's bold, I know. So, we're, as this says, building a scalable, heterogeneous computing library that has all the APIs that users and package authors need, with a sensible and consistent design that all builds on a simple task API. So I'm going to do a quick show of hands. Who here has implemented an algorithm that uses multi-threading successfully? Okay, thank you. Same question for distributed computing, multiprocessing. Show of hands. Okay, and for GPUs? All right. How about all three at the same time, successfully? Okay. I was hoping for this. So, the assertion I'm making today, doing that, combining the three of those is easy with Dagger. Not really something that we've been able to do before. I have some code examples up here. Don't read into them too much, but we have the key point is we have a variety of APIs in Dagger that basically can do this. We have tasks, the basis of everything in Dagger, but we also have things like arrays, where we have our D array with distributed multi-threaded GPU operation for just basic simple stuff, matrix multiplies, broadcast, all that. Automatically handles all three of those modalities. We have data depths, this new thing that's kind of come out in the last year that allows really powerful scalable programming in Dagger. And also this new thing I'm working on, SPMD, kind of like MPI or CUDA, again, kind of looking towards this really heterogeneous scalable parallelism. So I wasn't prepared for the animations. Okay, so Dagger meets you at your problem. So unlike, some libraries, you may have to, with other libraries, you may have to fit your problem to match the library, right? I'm sure we're all familiar with this. It's like, oh, I have a nice algorithm. It's sequential. I want to parallelize it. Oh, now I have to tear my entire algorithm apart just to make it work. I will just read them. Thank you for telling me that. The thing cut off at the bottom under acceleration is multi-threading, multiprocessing, and GPUs. Thank you. So basically, the point is that Dagger meets you at your problem with APIs that are generic and sensible and you already use. Arrays, tables, graphs, supporting also kind of new stuff that still is very simple to work with, streaming and SPMD coming soon. And as I said, the three main modalities supporting all of these. Any API that Dagger has basically supports the three, and if they don't, file an issue. We should fix it.
Additionally, Dagger knows your hardware. So you may not know your hardware, you may know your hardware. Dagger is already aware of it when you say using Dagger. It knows about Julia workers, CPU threads, GPU devices of any kind, the various memory spaces that they all have, and any disk devices, the storage you have available. Additionally, Dagger measures a lot of really interesting stuff, like the execution time of the tasks you submit, the number of allocations they make, network transfer time, data locality. Obviously, you can't see those down there. Why? Because it wants to optimize the algorithms that you submit to Dagger. It wants to optimize the crap out of them. It wants to make everything run as fast as possible, and to do that, it needs to know everything about your system and everything about the problem that you're giving to Dagger. And additionally, Dagger is pretty convenient. We, in particular, have a lot of really useful features. A built-in dynamic, also heterogeneous scheduler, work-stealing load balancer, automatic data movement. All three of these automatically enabled by default. You don't have to do anything. And then out-of-core and checkpointing when your problem starts getting really big and you need to be able to work with data that just doesn't fit in memory or doesn't fit in VRAM. Lazy file loading if you have a ton of files or big files and you only want to load stuff in on demand as necessary. Fault tolerance if distributed.jl decides it's just going to give up and go home. That's okay. Dagger will handle that just fine. And additionally, logging and visualization so that you can make pretty plots about the wonderful scalable performance of your algorithms. And if you saw the workshop, you may have seen some of these. So why not some other parallelism package that exists in the Julia ecosystem? So real quick, time check. So most packages, not just parallelism-specific packages, but most packages try to solve their own problems, right? Domain-specific stuff. I don't know, maybe you have an ODE solver library and it rolls its own multi-threading, it rolls its own distributed GPU, all that, and that's okay. But it doesn't necessarily compose. In many ways, it may not compose in terms of Julia's generic APIs. It may not compose in terms of performance. You may have an ODE solver, but you may also have a machine learning model in there. And do the two know about each other? Do the two operate efficiently together? Often not always. And what also happens is that the domain specifics that those packages handle and the parallelism that they implement become non-separable. And so you can't actually necessarily reuse that parallelism. And of course, you can't necessarily as easily build features into that parallelism like the ones that Dagger has available. So basically, we end up with many different infrastructure solutions for parallelism, and we re-implement the same algorithms again and again. Sometimes they're reusable, but sometimes they're not. Even though that's kind of the goal of Julia's, write an algorithm once and it's generic and reuse it, but that's not always possible when it comes to parallelism. So for reference, users here, when I say users, that's all of us. That includes me too. That includes package authors. That's a generic term for everyone here today. We all get confused when we're deciding, what package am I going to use to parallelize a given problem? There's a lot out there. I mean, even for me, when I'm developing Dagger and I'm adding some new modality, sometimes I'm like, actually, what should I use? Do I need to roll my own, or do I need to grab something that's out there? Can we settle on a single foundation? I mean, I know it's a big, bold statement to say, hey, maybe we should just kind of pick one thing. Maybe we can. Maybe it's a good idea. Now, and again, my suggestion is that Dagger is that one foundation. Now, there are some barriers to this. We have, so just quick overview of what we have. Let's go one by one. So in terms of overhead and memory usage, so if you were at the workshop on Tuesday, you're aware of this, and you may have heard little bits about this from me if you've spoken to me as well. Dagger has overhead, always is going to have overhead. Any abstraction you use will have overhead, but most of this is incidental. I mean, 95%, I would assert that probably 95% of the overhead in Dagger today can be removed with the application of some basic software engineering skills. The reason why there's this overhead, when you make decisions like using dynamic dispatch within your scheduler for good reasons, Julia's compiler can't help you as much, so you got to do things like caching and memoization and all that stuff you're on your own. And I'm doing that now. If anyone wants to help, if anyone feels like that would be fun, please message me. Missing algorithms. So, of course, if you're going to use a parallel computing library, you need algorithms that work on top of that actually solve your problems. Linear algebra, MapReduce, broadcasting, slicing, indexing, whatever you need, those need to be available, right? And, of course, we need to write those, but we need people who know how to write these. I mean, I can tell you how Dagger's APIs work, but I can't tell you how to implement I can tell you how to do Cholesky, but I don't know how to do LU. I don't know how to do SVD. I need people like you, people in our ecosystem, to implement these. So we need more contributors who know how to do this. And, I can guide you on how these APIs work. They're somewhat documented. We're going to talk about that momentarily, but, we need people who are willing to do this. Now, the barrier to that is documentation. If we're going to have a universal API, a single foundation, it needs to be well documented so that I'm not the bottleneck for telling people, how do you use Dagger? You should be able to go to the documentation and see, oh, okay, this is how all of this works. Our documentation is lacking. Our examples are lacking. And again, I would love help with this. We want to make Dagger into something where it can scale not just to hardware and software, but also to the contributors and to the people who want to use it and develop it and improve it. If you don't have this, users are like, I don't know how this works. I'm going to use something else that's documented. And that's unfortunate, and that's something we can fix quite easily. And finally, consensus. So I made this big, bold statement. I know probably a lot of people are in the room are thinking, I don't know. I don't know if I'm willing to commit to Dagger. That's understandable, but I think we need to have a discussion about maybe starting to centralize on something, whether it's Dagger, whether it's something that might look similar, somewhat different to Dagger. We should start finding something that we can all build on, because if we're re-implementing the same stuff again and again, and this package works with these kinds of acceleration, but not these other ones, and this one is got a different set, and they're just not performance composing together. I mean, we can't write scalable code easily. We have to resort to rolling our own everything, just like they do in all those other languages. I won't mention them. And this is the end of my talk. I would say if anyone wants to discuss this, I'm leaving a lot of time for discussion. I would be happy to discuss this, positive, negative. I'm really interested to hear what people think. So that's it. Please give Dagger a try if you haven't already. If you have in the past and have been unhappy with it, give it a try again and reach out if you run into trouble. And of course, contributions are always welcome. Thank you so much for listening.
Great, thanks a lot. And we have quite some time for questions.
So, thanks. Dagger's pretty cool. I know of other projects that have parallel task tuning heuristics like Futhark. Really cool small language. But it's based on a more restricted language, and then they can compose it and make all sorts of interesting proofs for the compiler to specialize on because it's built on Haskell. Mm-hmm. Are there any big semantic or type theory barriers in Julia that would prevent Dagger from being way cooler, way more powerful that you know of?
Yeah, that's a great question. So I think that there's a few areas where the answer to this could be yes. I think for the most part we don't actually have too many problems with this, and the reason why I think that's true is that we have a lot of very powerful reflection capabilities, the ability to take a block of code, add a macro in front of it, you can see the AST, but you can also dive down and start seeing all of the internal IR, all of the LLVM, all of that. So if you want to go and do really cool optimizations with Julia, we have the tools to do this. So there's no reason that what I've talked about here today couldn't also be something that is more generally applied as kind of like, maybe a compiler optimization or something like that to automatically scale code without even having to deal with Dagger-specific APIs. I assume this is kind of maybe what you're asking is like, can we have this just for big blocks of code, just say, make this fast? I think something like that is definitely possible. Yep. Thank you.
Any other questions?
So one of the things that have made me hesitant so far to use Dagger as a primary processing framework was that the load time is quite high. So depending on Dagger currently has a high impact, but the thing is you cannot, if you have an extension, then you again have to have an execution mode, and then you have to say, oh, if execution mode and Dagger is loaded. So can this be done on a medium to short time frame that we get the load time to, I'd say, 10 milliseconds or something that package authors will really say, yeah, I can take this on, because otherwise we have this chicken and egg problem. Oh, it's a heavy package, I don't take it on, but nobody's using Dagger. So is there a path to at least have a lightweight core of it or something that we can depend on?
Yeah, and that's great. That's actually a barrier to adoption that I really wanted to talk about. And I've had a little bit of discussion about that today. Yes, we package authors especially are not going to want to adopt something where they're kind of hamstrung, they're stuck with just one approach, and if that approach falls short of its goals, which happens, they don't want to be stuck. It's my belief that the generic APIs that Julia provides to us can somewhat solve this issue. I mean, let's talk about, arrays. I mean, if you're not happy with Dagger's D array, just switch to a different kind of array. I mean, if you write generic array code, this is totally possible. Similarly true for a variety of things. Data depths in particular, I'd like to mention, though, because that's one of the big things that we've been developing this year. That's something in talks with Sergio up here in the front. We're considering that, hey, maybe we should add a more generic version of this API, which is quite powerful. Maybe we need to add a very small base package that just implements the API, but also have backends not just for Dagger, but also for sequential execution, for debugging, or if you want sequential execution, quite easy, naturally transforms into that, but also multi-threaded, potentially also just distributed or just GPU. No reason we can't do that. I'm honestly very interested in that because that is a big barrier to adoption. Anywhere else where that's the case, if you find that when you're looking at Dagger, please report that and suggest that. I'm very open to having interfaces which are not Dagger specific but can be powered by Dagger when Dagger is loaded. Yep, thank you.
Any other questions?
Thanks for the talk. 2 questions. First question is short. Is the scheduler NUMA aware? And second question, how much of the dynamic scheduler can I turn off and switch to static scheduling? So basically analyze my hardware up front and then run statically.
Yeah, great questions. Thank you. So the first question about NUMA awareness. So Dagger is not currently NUMA aware. And that will lead to reduced performance if we end up ping-ponging memory between NUMA domains, which obviously we don't want to do. So what I've been working on very heavily, and I have it's basically a local development branch, is an entire overhaul of the scheduler, not an entire overhaul, an addition of programmability to the scheduler. Because right now, all of the logic of the scheduler is pretty hard-coded. On this branch, I'm basically switching to a more programmable, more flexible system, and in that system, we could quite easily define NUMA awareness as part of the overall cost function that Dagger's scheduler computes. So and the idea would be that we add an implementation of NUMA awareness. We say, okay, thread 1 and thread 2 are not exactly identical like Dagger tends to treat them, but actually what NUMA domains are they on, especially considering thread pinning. Where is a thread pinned to? Okay, now we can say what NUMA domain is that, and actually add that awareness. And then to get to your second question, Dagger's default scheduler is dynamic, but the data depth scheduler is static. And so if you use data depths, which I highly recommend for writing algorithms, you get static scheduling. And Shemek up here in the front has been working with me on a very powerful new scheduler that we're planning to integrate that uses a proper optimization model to do full-on static scheduling. So definitely be on the lookout for that. Thank you.
Maybe a related question. I assume as the system gets big, the single central scheduler will at some point become a bottleneck.
Yes.
Is there a path to a system where we have like sub-schedulers for sub-parts of the graph that say, okay, now this scheduler first will schedule locally, but if the node is really overloaded, then it'll pass the work back to a higher level scheduler to go to some entire other...
Yes. This is also something I have a development branch for. Again, I don't like to merge development branches that are kind of not yet ready to go, so I've got a lot of features that are in progress, but that is definitely one. Notably, the first part is distributing the scheduler so that the scheduler runs on each worker rather than just worker 1. I already have that working, I just need to get that ready to go. And that will alleviate a portion of the problem. Also, work stealing and work sharing across workers will also assist with that and reduce those bottlenecks. Sub-schedulers, we should talk about that in more detail. That is definitely something that I've thought about and I think could be quite powerful, especially considering the new programmable scheduler framework I'm working on. And so, yeah, that would be a possibility. And basically could be something you could just implement and plug right in. But if it works out well generically, we could just add it to Dagger. Thank you.
Thank you very much. And thanks to the speaker again. It's time for our next talk. So, our next speaker is Benedikt Geyer from the University of Cologne, and he will tell us about libtrixy, an approach to inject some new Julia code into some big monolithic Fortran code bases.
Ja, ich nehme das. Kleinen Moment.
I messaged you about the JLL wrapper issue with Alpine. Do you want to discuss that later or now?
All right, I think I can get started. Okay, so first of all, thanks for the great opportunity to speak here in front of such an experienced audience. Yeah, as said, this talk is about libtrixy. And, okay. Well, give me a second. Okay, why not? Okay, I'll do it like that. Okay, so libtrixy is an interface library to the computational fluid dynamics solver trixy.jl. And trixy.jl is written in Julia. And the interface we now want to come up with is an interface from C, C++, or Fortran to Julia. And that might be the most unusual thing here. And we plan to use that for HPC simulations and Earth system modeling. Yeah, these guys are sitting over there on the other side of the floor, unfortunately. But yeah, nevertheless, these are our applications here. Yeah, and I will walk you through why we do need such an interface at all and how we did it and what we're currently doing with that. Okay, so why? Of course, there's a project. It's called Adaptex. That's an acronym. It has a really large title. And it's, of course, on Earth system modeling and making it exascale ready. And I could go into details here, but I won't. Instead, somebody else did that. So last month, I was at Zurich at the PASC conference. And there was a very interesting talk by Chris Maynard from the Met Office UK. Yeah, and he basically nailed it. That's just a screenshot of his talk. That's not in my official slides. So he was talking about the old approach they had in their code, in their dynamical core, and what they're currently doing. And so he used, so he said, there were these great old times where you had a high-level language like Fortran, which the domain scientists could use for writing up their mathematical model in a very concise, textual manner, which everyone could understand. And then you had a very powerful compiler, which would then transform that to machine-specific instructions, and you had performant code. And as he remarked, that's a nice separation of concerns for domain scientists on the one hand side and computer scientists on the other hand. And now you have all these other things. You have GPUs, memory, performance, all these things you have to care about, and that breaks essentially this separation of concerns. And of course, there are lots of tools to help you with that. But in the end, of course, still a domain scientist would need to know about all of this stuff. He would need to be educated in how to do it properly. And yeah, maybe that's not what he essentially wants to do. So that's a nice picture here. So his claim was things should be more simple again. And okay, there were lots of people at this conference from all these institutions doing climate and weather modelings. And what they usually have in mind is to come up with kind of a generator approach where you, for example, use Python to generate code in an intermediate language, and you then compile that code to efficient code. But yeah, thinking about that once again, so on the one hand side, a high-level language, and on the other hand side, efficient code, and that's Julia conference here, right? Okay, so why not do that in Julia? That's our idea. Yeah. We have Trixie on the one hand side, our main program on the other hand side, and we have our library in between, and that is composed of a Julia part, a C, and a Fortran part, and yeah, I will just quickly walk you through. But first things first, Trixie.jl, that's the flow solver that we are connecting here. It is a simulation framework for conservation laws. It's built around an adaptive, high-order, discontinuous lurking method. Let's say one of the outstanding features is the entropy stable and entropy conserving methods that it implements. And yeah, our community and also our features have grown considerably large during the last years. Yeah, here's a QR code if you're interested in that. And we also have a YouTube channel. And of course, okay, yeah, that was just to put the VLAN to a test, but also that works. Okay, great. Yeah, so that's, for example, that's a demo of the adaptive mesh refinement features you have in Trixie. All right. Okay, so now I'm lost in YouTube. Okay, so continuing with that. So now we are on the right-hand side still. So that's our interface, like on using Trixie.jl for an actual simulation. To set this up or to configure that, we have Trixie as a library, so we do the configuration through code. And the code is what we call an elixir, and it looks like that. So going up here. So you have, of course, to include Trixie, and also now libtrixie here, and then you can specify your equations, the solver, a mesh, initial conditions, and then you put this all together into an object that we call a semi-discretization because of the PDE we want to solve. And then you define the time span, and we have a routine that's called semi-discretize, which then transforms this to an ODE object, and that can be passed on to ordinary diffie. And then this does the integration in time. And now here for libtrixie, we pack all these things together into an object that we call a simulation state, and that is something that we save. All right, that was the first part. Now we come to the interface. And here we have, at first, a Julia API. So a Julia API to Trixie.jl, which is also a Julia code. But the reason for doing that is that we have we need to somehow translate the complex data structures that we have in Trixie. And so the final goal is you have to kind of come up with an interface which has just these integral data types that you can then pass around when calling that from C. So it typically works like that. So for example, you want to get the number of elements. We have such routines here in Trixie, which then get these objects that we put all into the semi-discretization object. It kind of unpacks them, and then you can call these internal routines that are there in Trixie. And that's maybe the most interesting part here now. On the Julia side, we use this base C callable macro, and here below the add C function macro to get a function pointer to this routine that we just implemented in Julia. And what it does, it fetches this simulation state, and then it just calls the Julia function that we defined up there. Okay, so the next building block is then the C API. So we just have these, we just generated these Julia functions, which are C callable. And we now have to remember the name that we gave to these functions, so these C function calls. And now on the C side, we can now here use the Julia C API to just evaluate the string that I put here in the first line. And Julia will evaluate the string and will then return a function pointer to this internal routine, and it comes as a void pointer, and we store it on the C side. Yeah, later on, if you then actually want to call this function, you of course have to get this function pointer once again, and then you can really cast it to the to your actual functional syntax, and then call the function. Yeah, that's the C API. Our next part is Fortran, and that's rather simple because once you have a C library, calling that from Fortran is rather easy. You just have to write this interface around that. Okay. So of course that was tedious. So there were at least 4 points where you, 4 different files, maybe more if you include header files, where you have to kind of put these things together and remember all the names and have it done consistently. And yeah, but on the other side, it's really easy to do that. So I call it genlibtrixie.jl, working title maybe. So that's in the end a helper script which just takes such a YAML file where you specify how it should be called and what the docs are like and what the return type is like. And then it generates all this interface stuff with some gap texts where you have to-do markers. And that are the places where you actually have to do something, where you need to think about, like actually calling Trixie functions. Okay, so how to use this library in the end? It is a CMake project, so you can just configure and build it. And yeah, for writing your main project, so to say, you have to, in case of Fortran, include the model, of course compile that, and link it to libtrixie SO. And that, for example, in the most basic form could look like that. So you include libtrixie, you have to initialize the Julia runtime environment, you have to initialize the Trixie simulation, and then the most simple main loop would be this, like, if it's not finished, then do another step. And then you have to finalize it at some point. Yeah, and that's it. So it's an interface library. Of course, it's interesting if it impedes performance. Of course, it does not. So we have some very simple benchmark problems here, one in 2D and a moderately sized one in 3D, just implementing the compressible Euler equations. And yeah, for this small example, you can see that, of course, there's an overhead. But if you move to a, let's say, reasonably sized application, then it does not matter anymore. So that just tells us that libtrixie is kind of as fast as libtrixie.jl, which is just the Julia interface, which is nearly as fast as native trixie.jl. And that's good because because we already know that the performance of trixie.jl has been shown to be on par, or maybe even better at some points, than classical codes, so codes written in these classical HPC languages. Here's the reference. All right, just want to show some results. So our, let's say, most loyal customer, and also the only one, is Massey. And that's the Modular Earth submodel system. That's one of the cooperation partners in this project I mentioned in the beginning. And that's a large framework which couples physical model, dynamical cores, all those things. And it's written in Fortran. So they actually want to use Trixie now as a kind of replacement of the current dynamical core, which is known to, for example, not scale very well and not be GPU compatible and things like that. Yeah, here is the baroclinic instability. This is kind of a standard test case in atmospheric flows, and you have seen the video on the first slide. Okay, so it's not a very large test case. It has very few cells, but as the polynomial degree is high, you get this large count of degrees of freedom here. And yeah, we can now, of course, run that on a supercomputer using libtrixie. And these are experiments that we did at Jülich Supercomputing Center. And here you can really see that it scales very well. And that's, of course, not my achievement. It's the achievement of trixie.jl, but we can now directly use that here. Yeah, and another thing I'm really happy about is that we now can also leverage GPU offloading capabilities. And that's really bleeding edge. So it was just last Tuesday when our student Lars announced that he finally did his first draft of a multi-GPU version of trixie.jl. And that's based on CUDA-aware MPI, on kernel abstractions, and on adapt.jl. And what I did here is I just took the same example, the baroclinic instability that we have seen before, and used exactly this problem with the same size and ran it on 1 GPU, 2 GPUs, 4 GPUs. So not this massive GPU counts that we have seen before. And also, of course, I have to mention that the scaling is not ideal yet. And also the numbers on the y-axis here are not the same as before. So it does not compare well to the CPU implementation yet. But of course, as I said, that is work in progress, and Lars already figured out some places where our data structures kind of interfere with making this highly performant. Yeah, but the cool thing, and that's my main message here, is that it works. And if you think about this nice switch that we have seen on one of the first slide, so here's our code, the semi-discretization, and now we have this adapt to Q-array keyword here, and if you do that, then GPU offloading is enabled. So GPU offloading on, off, things like that. I really like that. So what's the time?
5 minutes.
Okay, so can take some time to tell you about our next step. So what are the things that we are going to do next? First thing that's already there in Trixie is adaptive mesh refinement. And of course, we would like to use this here. So this is the first try to run that for the baroclinic instability. So when the instability comes up here, you see that we get refined elements here. Unfortunately, so this is actually a 3D test case. So it discretizes the whole atmosphere. And if we get these non-conforming interfaces in the vertical directions, then our DG scheme sometimes develops some instabilities with this. You have a hydrostatic balance profile there, and that seems to cause some issues. And of course, we will now look into this because we are really convinced that AMR would be nice to have. And as said before, we of course would like to improve the multi-GPU performance. And then we will look into more advanced models for atmospheric flows, because right now for messy sites, that's kind of a toy problem. They just started and are happy with the results. But of course, we would like to get some real mutual coupling. So integrating their physical models and our flow solver. And in order to do so, we have to extend Trixie a little bit. And we also have a sub-project for that now. It's called Trixie Atmo, and that has also been just started. Yeah, that was another point. Also in my abstract, I announced that we did some experiments with a package compiler, and we did that, and it worked. But our executables were quite large. But we had this nice talk here on new ways to compile Julia code, and there was also Julia C mentioned, and that seems really attractive to us. Because so we have Messi as our main customer, and they are non-Julians. So when we tell them about that they have to set up this Julia runtime environment, and sometimes it might fail due to some reasons, that might scare them off. So if we can at some point tell them, okay, there's just one shared object, you have to link it, and you do not need to care about anything else, they will probably be happy. And some final thinking here. So for these atmospheric simulations, single precision should in principle be enough. And we are currently working on that. So I'm not working on that, but fortunately we have other people working on that. that will make it possible to do the whole simulation in single precision, and that will allow us to use like prosumer GPUs, because we, at least in our institute, do not have these data center GPUs available. All right, yeah, final slide. Thanks a lot to Julia community. So I just started that last year, and so far it has been a real pleasant journey. And as I told you, we are using lots of these incredible packages. Thanks to the Trixie community. Also, as I told you, that most of the things are not my achievement. It had already been there. I just had to be adopted in this interface. Thanks to Michael, who had come up with this idea for libTrixie. So when I started, basically, he had already figured out all the technical details for that. Yeah, thanks to Lars for his multi-GPU implementations, which he finished last Tuesday. And to JuliaSQL Computing Center for the resources. We have a reproducibility repository. It's at this URL, and in the QR code below, the QR code on top is for libTrixie itself. Yeah, thanks for your attention.
Thank you very much. Are there any questions? So I think Boris was first.
Do you have an issue with the garbage collector interfering when you call Julia many times from C?
As far as I can tell so far, we did not have any issues.
Okay, and yeah.
If it's successful with the Messi collaborator, would that be the majority of the compute, or do they have lots of back-end algorithms?
That's a good question. So when we had our discussions with them, they would usually tell us that they have some chemistry going on, and that also seems to be a large fraction of the computational time. But yeah, the motivation for this project was that the dynamical core that they currently use, which implements a spectral element method, that this is not capable of running on current supercomputers, and especially not on the upcoming generation.
Okay, it's even better, like it's too big to even work.
Yeah.
Okay, great.
Are there any other questions? Yeah.
Thanks for the talk. How would you manage the dynamic load balancing from the C side? Is this something that Trixie does, so you can just profit from it in these future steps that you were mentioning?
Exactly, yeah.
Okay.
It's all supplied by Trixie, yeah. It has this meshing backend pforest or TET code in the future, and that does all the balancing, yeah.
Okay, thanks.
Then one last question, and the next speaker can already set up everything.
I have a question about the least CPU intensive part of the process, generating the wrappers. I liked what you did with the YAML file. Do you think that, I mean, it looked as if that would probably even be quite generalizable, because writing boilerplate code is never fun.
Yes.
So anything that we can make a bit easier would be dead useful.
I'm sorry, and your question was about the speed
well,
of that?
is it, you know, this genlib Trixie, if I remember the name
It's just
correctly.
a working title. I mean, it's just
Yeah,
a script
but-
that I have on my laptop.
But it was just, it just struck me that I mean, it's a simple thing, but it's also quite an annoying thing to get wrong. It would be quite nice if that was, you know, just like generate C Fortran wrappers, and
Okay.
it could work for anything and for anybody.
Yeah, thanks for the comment. Yeah, and that's not yet done, so it's very specific for my personal use case. But yeah, of course, in 90% of all the cases it just works, and in the other 10% I would have to figure out. Yeah.
Oh, great. Thank you for the talk again. Now it's time for our next speaker, Giacomo Aloisi from Switzerland. And he will tell us about seismic waves.jl, wave simulation package in Julia.
Perfect. All right, check. Does it work? Hello. Perfect. Okay, so my name is Giacomo. I come from ETH Zurich, and today I'm going to show you what I've been working on for the past year or so seismicwaves.jl. And this is in collaboration with other people from our group. And special thanks to Andrea Zunino, which is my supervisor, and helped me set up all this process. I'm just starting my PhD, so I'm really getting started to know Julia and know more about it. So bear with me. All right. So what is seismicwaves.jl? It's a package for wave equation simulations, and it's in a suite of packages called HMCLab. And this suite of packages is designed to do inversions using Hamiltonian and Monte Carlo approaches, so probabilistic approaches. And there are some other packages which are available now. Iconal solvers is one of them. There are Monte Carlo samplers and others. But today I want to focus on, well, what I develop. And so, as we said, we are simulating waves. And waves come in a different ways. We have acoustic waves, we have elastic waves, we can also have viscous terms. Yeah, so it's quite complicated. And what we want to do is we want to scale using multi-XPUs, yes, but for a specific reason. We want to solve the problem of full waveform inversion. And this problem has been used quite a lot in the seismic tomography community to basically do an image, take an image, a shot of the Earth. And that's pretty cool, in my opinion. And we do this using multi-XPUs. And so we're using a bunch of packages that have already been talked about: parallel stencil, implicit global grid. All right, I will give you an introduction to full waveform inversion, which is, well, a very cool way of reconstructing the Earth properties. So say that we have a domain in 3D, and we want to reconstruct the wave speed, in this case, this parameter c. And what we do is we have some sources somewhere. We know the position of those. We know the characteristics of these sources. And we have some data from receivers. And this data often looks something like this. So a seismometer, and we have a seismogram. So how do we use this data? So we want to simulate our own waves that passes through this domain, and we want to compare the data with our synthetic computations, and then do some type of minimization and find how to compute the gradients with respect to the velocities, and then to invert for them. And so, as I said, applications, well, the main application is seismic tomography. So here we have a picture of the Japan Trench, and there's a bunch of work being done to reconstruct how the plate look like under the surface. And another application in a much lower scale is ultrasound medical tomography. So in this case, there's a guy in our group, it's called Patrick Marty, and he's working on transcranial ultrasound computed tomography using these methods. And so we really want to have a fast way to compute these waveforms, and we want to have a very high accuracy as well, because we want to resolve small details, and we also want to have high frequency data, and high frequency data need very small resolution. Right, so the theory and implementation of this. So we need to solve wave equation. So these two are acoustic equations, one with and one without the density terms. Another wave equation we are interested in is the elastic wave equation. And this one, for example, is the stress velocity formulation isotropic. So we have three terms: the density rho, the lambda and mu parameters are called Lamé parameters, and they relate how the pressure waves and the shear wave velocity are. All right, cool. But how do we do this? So once we solve the wave equation and we solve the forward problem, then we need a way to compute the gradients with respect to our parameters, right? And so what we do, so in this case, we're going to look at some misfit functional, chi. And this misfit functional, we assume that we have some observed pressures somewhere. So we are in the acoustic setting now. And we have our synthetic pressures. And we define this misfit functional, which is in this case just an L2 norm. We want to compute the gradients, as we said. And we could do finite differences, but this would take a lot of time, because to compute just one derivative with respect to one parameter, it would take 0.4 seconds. But if we have a lot of parameters, it would take 444 hours. This is not feasible. So what we do is, of course, we use some kind of trick. In this case, we don't go through the automatic differentiation, but we use the adjoint method. So we need to derive the adjoint equations, which involves the Lagrangian, differentiation by parts. And then we get that our equation of self-adjoint. That's great, because we can solve them using the same method as we solve the forward equations. And we now have a source term, which is related to our misfit functional with derivative with respect to the pressure. Right, cool. And then we can compute our gradients with this integral if we can compute p and lambda, which in this case are the pressure and the adjoint solutions. And now the time to gradient is much, much less. So we can compute one in 1.8 seconds, which is pretty cool. All right, so all in all, an FWI recipe involves choosing an initial model, solving the acoustic wave equation to get our pressure field P, then we compute the misfits and the adjoint source, we solve the adjoint equation to get the adjoint field, and we compute these gradients while solving the adjoint equation. And then we use these gradients with an optimization algorithm to reduce our misfit, and we go back to step 2, we do all over again. And this is a deterministic approach, and the probabilistic approach is a bit more complicated. I will not go into the details on how it's done. But yeah, so this is FWI in a nutshell, basically. And so seismic waves, how to use it. You can download it if you want. You can install it right now. You have to add this registry, which is JuliaGeoff, which I will show you in a second. And this contains a bunch of software that my group develops. So iconal solvers, we talked about this. We also have some geopolygons, some MC sampler, some magRev2D-poly. So that there are some packages which are still in development, and seismic waves is one of them. So what I would like to do now is to do a bit of a demo to show you how to use this package, because I think it's cool just to see how easy it is to run a wave simulation with our package. So I have some code prepared. So we need to import our seismic waves. We are going to plot something as well. And we have some numerics. And this numerics is like, yeah, we have to choose the number of time steps we want to run our simulation, the delta t, delta x, delta z, and the size of our grid. And then have prepared some setup, which is hopefully going to plot here. Very cool. And here, so we have this 2D setting where we have one source, this little red star here, and we then have a velocity model which is increasing in depth. So the velocity is increasing in depth, and we have some receivers on the top. So now if we want to run our model, we need to do something. We need to declare material properties. In this case, we are interested in the VP, which is the velocity of pressure waves. Then we have some boundary conditions. In seismic waves, we have implemented CPML boundary conditions, which are absorbing boundary conditions that can dampen the wave on sides of the domain where we have prescribed them. And then we put it all together with the input parameter acoustic, and we run our forward with SW forward. And this will take a bit of time because it needs to compile, but after that, we can save our results in HTF5 file. And what we get is something like this. Let's see if I can show it to you. Maybe I need to do this. All right. So we have our shot and we have our time steps, and we can see that our wave propagates in time through the domain and kind of this and it gets absorbed when it gets to the boundary. So this, I guess, was pretty cool to show, like in a few lines, how you can do what you can do with this. And let's not forget that we are here for the HPC part. So the HPC part comes into play when we can choose the parallelization type that we want to run our simulation for. So in this case, I'm using multi-threading, but here I could change this to CUDA, or I could change this to AMD GPU. And if I can do using CUDA here, it will allow the seismic wave package to load the extension for CUDA, and then we can run this with CUDA, for example. And I don't have it in my laptop because it doesn't have an NVIDIA GPU, but you can do this. And so the only way you can, well, the simplest way for us was to add this flag, which is very similar to what I've seen before in the previous talk. So I guess that's cool. Right. So back to the presentation. So we've already talked about parallel stencil. It's a pretty cool library. This is what it looks like in the code. These are the kernels, kind of a snippet of code with the kernels. So we have these macros parallel. We have these parallel indices to tag our functions. This is pretty cool, I would say. I really like working with parallel stencil. And then we have implicit global grid to do multi GPU computation. So then we have our ID communication. We have update halo that makes the communication possible in between the different devices. Super cool. Now we have just a few minutes left for experiments and benchmarks. So what we do usually for benchmarks is we try to invert this model, which is called the overthrust model. It's quite complex. It has a lot of sharp interfaces, and it's kind of a standard for geology models. And so we try to invert that using our package. So here I'm going to show a little animation of the inversion process as it goes. So we have our current model that is just a gradient, as I showed you before, basically. So the velocity is increasing with depth. We don't know the features that are under there, but we know that it's increasing at least. So this is our kind of prior model. And we then run our inversion, and there we go. So we see more and more and more. Our misfit decreases, and it's pretty nice. And of course, it's not perfect, because in this case we add some noise to the data we have. So it's kind of, it shows that our package is kind of stable to noise as well, which is pretty cool. All right. And now let's do 3D inversion. So same model, but just extruded in 3D, just bent it a bit. So now it's a bit bent. And this is the setup with sources and receivers. And this is a side view, and this is, again, the kind of inversion process as it goes. So it kind of finds where the interfaces are and kind of reconstruct it kind of nicely, I would say. There's noise in the data as well, so it cannot be perfect. But yes, so this is pretty cool. And then we can see that most of the features are, even at very kind of low depths, are kind of resolved. So this is nice. Right, now to the benchmarks. We still have a long way to go in order to make our code very efficient, but still, it's amazing how you can be almost at the top of the peak performance with parallel stencil just by using it alone. So we didn't do any sort of optimization with that. We just stick to the parallel stencil, and we can see that in 2D we reach almost 100% of 90% of the peak performance for 2 different types of GPUs. One of them is like a consumer GPU, like RTX 4070, and the other is the A100. So it's pretty cool that we can also have our own kind of workstation in the lab and use it with this, and not only go to supercomputer, which is also cool. And if we go to supercomputers, then we can also do the weak scaling thing that has been shown in the previous talks as well. So we also show that we can weak scale quite nicely. And yeah, so I would like to give some conclusions now. So what are the features of seismic waves and the future of it? So for now, we have efficient scalable wave equation forward and adjoint solvers. This is all based on finite difference method, because we use parallel stencil, of course. We have reflective and absorbing boundary conditions. So seismic waves is fully written in Julia. It's multi-platform, portable, and it's usable with minimal explicit knowledge. I want to really emphasize this. Just changing a flag and adding, using CUDA or using AMD GPU allows you to do it on the GPU. Anyway, another thing I should mention is that we recently also have to support for arbitrary precision. So we can run in single precision as well. It's just a parameter of our inputs. So you can choose your precision. And if your backend supports also half precision, we should be able to do that. But Julia now is not, natively doesn't really support half precision yet, but we could in theory. Still work in progress are elastic solvers in 3D and anisotropy. We still need to work a bit on that. We only have 2D implementation of elasticity now and isotropic. The multi-XPUs implementations with MPI and implicit global grid are still kind of closed source. I'm still working on that. In principle, it's not hard, but I have to set up some infrastructure in order to do the gradients and to make the communication between the processes a bit easier for the user. And of course, we want to add support for more boundary conditions, misfit functionals, regularization terms to make the computation of gradients, well, applicable to more applications. And that's it. So I would like to thank you by showing you this nice simulation of elastic wave propagation in 2D that we have. And yeah, so thanks for the attention.
Thank you very much. So we do have definitely some time for questions.
Does it like seamlessly work with AMD GPUs? Have you tested it?
So I don't have an AMD GPU, and I haven't tested it, but it should be fine because the way me and Andrea wrote it is that you have this extension that gets loaded when you do using AMD GPU, and then it gets loaded and it's just Parallel Stencil supports AMD GPU by default. So we support it as well because of this. So yeah, should work.
Other questions?
Very nice work indeed. So I was wondering, you did a weak scalability test, and I saw that you have a 50% efficiency. And Ludovic just before showed a 93 or 97% efficiency. So do you have an idea?
Yeah, so the plots are different. So the plots are different. So I like to think about the scaling efficiency compared to your single GPU efficiency. And since we are 59% on a single GPU, yeah, we start from there. So the plots are different. They show different things, right? It's not the time with respect to the serial one, but it's the performance with respect to the serial one. So yeah, so that's why it's lower. But the thing is that it flattens. That's the only thing that matters. Well.
Other questions?
Yeah, one question related to that. So you said you still need to work on the multi-GPU code. And so you said you're using MPI plus implicit global grid, which you can combine, right? And so what is exactly that you need to do with MPI that you cannot do with implicit global grid yet?
Well, the thing is, I don't want the user to know about MPI, but at some point you need to collect the gradients. And you need to collect all the information from the nodes or store it somewhere. And yeah, so that part of the infrastructure of seismic waves, which is it's the high-level API, it's not yet ready, but it's gonna be coming soon. But it's just that I didn't have time to work on it. But let's say the backend part, it's done. It's only the user part, how the user interfaces with all this stuff, right? Because the user has to call MPI execjl on the script. So the user needs to know how there is MPI, but also I want to make it a bit oblivious. So I'm still working on that.
Okay, thank you.
Yep.
Are there any other questions? Look like from the audience? Then maybe I have one. Why a custom registry and not putting it into the general one?
Yeah, because well, me and my supervisor think that we are kind of not ready yet to be public to the world in the sense of adding our package to the global registry. But we're going to do that very, very soon. So I think it's just a way to develop our own stuff, and then we're going to publish it, like, definitely. But there is documentation now for seismic waves. You can look at the API, but there are examples, but the tutorials are not quite ready yet. So,
okay, great. Thank you very much.
Yeah, thanks.
So now it's time for our last speaker of the Julia for HPC mini symposium. Our last speaker is Bernard Font, kind of nearly local here, and he will present some work on a computational fluid dynamics solver, waterlily.jl.
Okay, this worked. Thanks for the introduction, and thank you for sticking around. It's the last session, and probably we are all a bit tired. So expect a bit of colorful fluid dynamics to cheer you up. And this is a talk about Waterlily, and Waterlily is a CFD solver for incompressible fluid flow that can do very cool simulations with moving objects and can run in different backends. So I will explain you how we do all of that. So just some background for people who's not very familiar with computational fluid dynamics. So we basically solve the Navier-Stokes equation, here the incompressible form, and you can see that there is a RE number here. This is the Reynolds number, and the problem we have with CFD is that for high Reynolds number, we have a very wide range of spatial and temporal scales that we need to solve, which means very expensive simulations. Here you can see one of these simulations of flow past squared cube, and well, all the scales that needs to be resolved in space and time are super, super expensive. So this is where HPC comes into place, and it's very important for CFD. So I don't need to convince you probably that doing Julia for CFD is a good idea, but I will just summarize it here. So first of all, of course, CFD needs to be fast because otherwise it's super slow. To run all these, simulate all these temporal and spatial scales. So it needs to be compiled language. So that's a check for Julia. We also need the language to have parallelization capabilities. And in Julia, we can do that at the shared memory level and in the distributed memory level as well with the different packages, which is also very, very important for CFD. So that's another check. And then we only need to run in the different architectures that are out there and that needs to, like, they keep coming out, and we need to be ready for those architectures. So again, thanks for the Julia community that's been working a lot on this. We have all these amazing packages that allows us to do that from a very high level point of view. So yeah, that's another check, and this makes Julia really ready to simulate CFD. Then on the other hand, we have added benefits to this. And of course, this is the solution of the two-language problem. Here we can integrate CFD solvers with machine learning libraries very easily. I've suffered this pain with other Fortran and C++ solvers in the past. And honestly, this makes it so much better. So I really appreciate this. And of course, the active community, like we are here in JuliaCon. I've learned a lot from other people, all the new developments, like engaging with core developers. It's super useful, and so that's very important as well. So let's talk a bit about Waterlily. So as I mentioned, we simulate incompressible fluid flow, and we do it in a finite volume numerical method. So we basically, our cells contain pressure and velocity information in a staggered manner, so we conserve mass locally. This is typical in finite volume methods. And we have an inverse boundary method to represent the solid interface of the problem. So here you can see there is a fluid domain and a solid domain, and then we have this interface that kind of smooths the solution from one to another. And this is the boundary data immersion method, which in short, what we need to do is to define a sign distance function, and then with that, and using the derivative of this sign distance function, which we can do with AD, we can compute the body normal, the curvature, and the velocity of the body, and then interpolate the effect of this boundary into the flow solution. This, what allows us really is to have very arbitrary prescribed motions of bodies that are shrinking, moving in whatever manner you want them to move. So we can do simulations which would be quite tricky when you need to do them in a body-fitted grid. So here actually we have a Cartesian grid that embeds this solid boundary. So the boundary can move freely, and we just take into the effect of the solid boundary through interpolation into the fluid. And a bit more about the numerical methods in Waterlily. So we have a geometric multigrid because in this Cartesian grid, it's very easy to implement this to solve the pressure Poisson equation. And we have a projection method to do the time integration for the divergence-free constraint of the problem. So this is just a short recap of the numerical methods. And now I want to talk a bit more about how is the setup done in WaterLily. So we have, let's say, 3 main containers. Here is a simulation that holds information about the fluid, which is another struct, and the body. And what we do is that by defining the size of the problem, the initial condition for the fluid, and the geometry of the solid boundary, if there is any solid boundary, then we have all our setup completed. For additionally, we can also run on different on the different backends, just changing a flag, let's say, as the previous 2 talks. So I think this is where this is going a bit for the users. It's very convenient to have just a single parameter that they can say offload to GPUs or just run in CPU multi-threaded or whatnot. So we have the same with the same setup with the memory keyword argument. And as you can see here, with just these very few lines, we set up this Taylor-Green vortex test case. This test case is just normally used for validation and benchmarking of CFD solvers. So you will be seeing some results about this. And you can see that we have this function, u lambda, that just sets the initial condition. Here is just some harmonic function for the velocity field. And then it returns a simulation with the resolution 2 to the power of whatever number we want. And then we can just time step this simulation object. And the time stepping just produces this evolution of the flow field. So as promised, we can do other geometries. Here is a donut. And the only thing we need to do to set up this test case is these very few lines of code. So we define where's the center of the donut. We define the outer and the inner radius. And then we just need to define the actual sign distance function through this body code block that you see here. And with only these very few lines, we have a geometry defined within our domain. Again, this returns a simulation object that we have a method for doing time stepping of the flow. And okay, we can do moving objects as promised. This is like an arbitrary jellyfish, I call it. So it's just a hollow sphere that intersects a plane that moves in a sinusoidal form and just shrinks and expands. To set up the simulation, it's just these very few lines of code. And what you need to do here is just to be a bit clever about the sign distance function, but also know that we can define different bodies. Here we call it autobody. And these have operations. These have an intersection operation with the minus sign between the sphere and the plane. So you create a new autobody that is the object that we pass to the simulation. And with just these very few lines of code and another call for doing the time stepping, we can run this simulation very easily. So let's look a bit about what are we doing behind the scenes to have this flexibility, right? So here is an example of how to compute the divergence or in a cell of our grid. It's very easy. It's just in finite volumes with Cartesian grids. It just looks like what comes in and what comes out of the cell, and this hopefully should be 0. When we want to implement something like this, the first thing we do, or we did actually before porting our code, was to define a macro that we call loop, that basically abstracts the loops whenever we need to use them. So instead of writing explicit loops, we just use this macro. And here, okay, it's not very useful for just one loop. You could just write it, and it would be doing the same thing as you can see here. But for example, if you want to pass some performance decorators to these loops or to running multi-threading, we were doing like just changing this macro. We would accelerate all the loops of our code. So that was pretty useful for us. Well, I haven't mentioned, but here for this divergence operator, we have a couple of helper functions. This partial delta, this just says, when I am in this Cartesian index, I look at the direction small capital I, and then go one step behind and one forward and see the difference. And we do this for the different dimensions of the problem. So you can see here also that this is multidimensional because we operate with Cartesian indices. So writing like 2D, a 2D flow solver or a 3D flow solver is the same. We don't modify our algorithms. So we did this abstraction, which maybe was out of laziness because we didn't want to code all these repetitive loops all the time. But it also gave us an advantage, which means that the computational load of our solver was now contained in this very small code base, this loop macro. So when we wanted to port this to GPUs, it was very easy to do this with kernel abstractions that were kind of an adaptation to this macro loop. So this is an adapted macro loop that generates kernels based on kernels abstractions.jl and calls these kernels. So we have here, again, a couple of utility functions for the macro processing, like grab and setDiff, just operates on the symbols of an expression. And this passes all the arguments to a kernel that is automatically generated in every loop in our code. And then we call this, as you can see here, with a specific backend. This backend is related to the user keyword argument memory that could be specified for array or Q arrays or rock arrays, right? So because kernel abstraction supports this. And to be fair, we did this porting of our CFD solver just in a couple of weeks or 3 weeks. And it was very easy. I did not have much experience on GPU programming before, honestly. And it's really, really amazing that we have all these packages such as CUDA.jl, kernel abstractions, and whatnot that we can, like, it allows us to port the code that would be quite tiresome in some other languages in a very easy fashion. And just with this, literally almost this change, we were able to run on GPUs all of a sudden. And as we will see later, this gave us a huge speedups. And well, guess what? Our code base went from 1,000 lines of code to 1,000 lines of code, more or less, because these were more or less the added lines in the code from the adaptation from one macro to the other one. So it's pretty amazing. You can see this is a very minimal CFD solver in terms of code base. So it's easy to, let's say, engage with us, contribute to the solver, and we always appreciate those. So let's look at some different test cases. We will be looking at validation, benchmarking, and profiling. Again, we'll be looking at the Taylor-Green vortex, as I've presented before, but also the sphere and a moving cylinder. And we will be seeing how the solver does on these different cases with increasing complexity from no body to a moving body in the flow. So first, validation of the Taylor-Green vortex. Here we are looking at the evolution of the kinetic energy and the evolution of the dissipation, or also the rotational energy of the fluid, if you want, for different resolutions of the problem. Here we go from 64 cube grid cells to 112 cube grid cells. And we can see that we are increasingly matching the reference, direct numerical simulation data, showing that our solver correctly solves the Navier-Stokes equation. This is the expected result. And actually, this fine resolution is the same as the DNS one, and we are matching it very well. So just to show that this is just not to, this is actually solving Navier-Stokes in the background. So it's doing the job. And then we tested a bit on the benchmarking side. What's the speed up we get when we run in multi-threaded CPU or in a single GPU compared to the serial execution. Here I'm showing for the Taylor-Green vortex on the left and the cylinder on the right, because the sphere is very similar to the Taylor-Green vortex because the body is fixed. And you can see that we have speed ups, which are the small numbers that you see on top of the bars, up to 8 times as faster for the 16 multi-threaded. So we are not hitting 16 when we have a 16 multi-threaded CPU backend. Maybe it's a bit our fault, maybe it's a bit kernel abstractions. I talked to Valentin, we will need to debug that a bit. But we are pretty happy with that. And then for the GPUs, this was tested on H100 in Mare Nostrum 5. We are very, very fast when we are filling up the GPU. And the speed that we get when filling up the GPU here on the bottom axis is actually the degrees of freedom of the problem, or the number of cells. So this is in millions. So for the moving cylinder, we go up to 300 million cells we can fit in a single GPU, which only consumes, like, for this single precision, like 39 gigabytes of memory. So we have a pretty good footprint, I think. And the speedups we get are like, for the Taylor-Green vortex, up to 200 times, or 155 for the moving cylinder. So that minimal change we did in the macro allowed us to get these crazy speedups, which is pretty good. Okay, let's talk a bit more about the cost. So cost in CFD solvers is measured as the time that it takes to solve the Navier-Stokes equation per degree of freedom of the problem per time step, right? This is a way to compare, like, I am faster or slower than other CFD codes, and so on. It depends a bit on the numerical method behind the scenes. So we have a finite volume, which is a low order scheme, but people that uses, for example, Trixie, that use the DG, or people using flux reconstruction or other high order methods, they have a more costly, by definition, by the numerical method, because it needs more operations, a more costly algorithm, but in a rough manner, we can compare to other CFD solvers. And you can see here, for the different grid levels that we tested before, and the different free cases, how does this cost evolve? So as we are filling up the GPU, our cost decreases quite a lot, from about 11 nanoseconds to here the lower one is 1.44 nanoseconds. This is in par, or actually better than other CFD solvers that are well established, like, I don't know if you know them, but NECRS or SOT2D. These are like Fortran CUDA solver, a Fortran with OpenACC solver, other C++ solvers we have other benchmarked against. Like, we are at least as fast. So Julia can be very, very fast. And this is a way that we can show it. Of course, we did also a bit more of profiling. So here you see the time that it takes for one time step on the different kernels of our code. So you can see the kernels on the right. Basically, we have scale U is just like a scalar operation on the fluid velocity, like a broadcasting. It's a very cheap one. You don't even see it. Here we have the big one. Project is the pressure Poisson solver. It's just a solver, like we need to do a solver of the Poisson equation, and this is the most expensive part of our solver in all of the cases. It's very expensive because here the test, as you can see, is single precision on my laptop GPU actually, and the problem of these linear solvers is that the reductions, I think, they are quite expensive, and we've not optimized those yet. So for us, this takes a lot of time, but this bottleneck is now identified, and we can target it to improve the algorithm. As you can see, adding the moving boundaries or a boundary or a moving boundaries for this cylinder, we increase the boundary condition cost. It's much more than I was expecting when I did the profiling. So definitely we need to try to tune that one as well. And on the other hand, like when we actually compute Navier-Stokes equation, this convective term and diffusive term through this kernel, the comp_diff, this is like let's say a pointwise kernel almost that only looks at these steps in the Cartesian index, like in the array through Cartesian indices. This is very, very cheap on the GPU. Like, you cannot even see this kernel almost here. So yeah, the bottlenecks are basically on the reductions on the GPU, I think. Okay, so quick recap. Water Lily is this very minimal code-based CFD solver for incompressible fluid flows. You can do crazy geometries, moving, deforming, whatever you like. You can run in this single flag. You can do serial, multi-threaded, and single GPU. We have very competitive cost, and well, actually in the presentation, maybe in the title, you saw that we had like it's a differentiable solver. Well, we got that actually a couple of weeks ago because we need to fix some functions about the types. But it works very well on the CPU backend, and we are now fiddling with the GPU because it was not working out of the box. Also, we were using forward diff, and we need to switch to enzyme more probably because it's now supported or will be supported by kernel abstractions on GPU. So that's our way forward. I've mentioned some of this. Then for those who know a bit about CFD, you may have realized that we have a constant resolution everywhere in the domain. Actually close to the boundaries, normally the flow has very tiny scales. So this means that if we need to resolve those, that same resolution is applied everywhere. This is super expensive, of course. So if you need to do like turbulent boundary layers and so on, it's very, very expensive. So there are a couple of ways to fix this. One is to have a formulation that allows you to have a very fitted or confined domain close to the body, which still produces like a physical solution. And this is through the Biot-Savart boundary condition, which basically is a prediction of the velocity on the ghost points of our domain, which is much better than the typical predictions that you do when you just do a convective outlet, for example. This is a work in progress that will be published soon. Then we also have plans for a volume of fluid method, so we can do multi-phase flows, and just some grid stretching, so we can fit these cells close to the boundaries as we need for turbulent boundary layers. And that's all. Here you have the QR codes for Water Lily or for these slides if you want them. And yeah, just enjoy the colorful fluid dynamics, I guess. Thank you.
Yeah, thank you very much. We have time for one quick question, maybe.
Yeah, thanks, Bernard. A very nice talk. Because you showed so many nice performance measurements, I wanted to ask, did you already try Julia 1.11 with your code? And did you see any performance regressions like we did?
No, I haven't. Okay, use this, sorry. I haven't tried yet because the benchmarks were in Mare Nostrum 5 and they have 1.10.4. Actually, that's on the CPU. Part of the cluster. On the accelerated part, they have 1.10.2, and that's the version that you saw here. I definitely need to test for 1.11, and I have a benchmark suite that very easily can run several Julia versions through Julia app, and you can check regressions or speedups. So that's definitely something I want to look at.
All right, thank you.
Great. Thank you, everybody. And also thanks to all the speakers of our nice Julia for HPC mini symposium again. And now I guess it's time for the last keynote down there. Thank you, everybody.